Welcome to another episode. If you're listening right now, wherever you are in the world, take a moment to tell me where you're tuning in from and what time it is there. It's always fascinating to think that while you're hearing these words, someone else, thousands of kilometers away, might be doing the same, maybe under a different sky, maybe even on the other side of the planet. And if you're new here, don't forget to subscribe so you can join us on future journeys through science, history, and the quiet wonder of the universe. Now, close your eyes if you can. Imagine yourself drifting above the Milky Way. Not the one you see on postcards or desktop wallpapers, that majestic spiral glowing white and blue across the darkness, but the real one, as astronomers have slowly uncovered it. Vast, dusty, strangely asymmetric, and still full of mystery. From this impossible vantage point, the Milky Way stretches nearly 100,000 light-years across, about 9.5 times 10 to the 17th kilometers. That's roughly 1 quintillion kilometers, or 600 quadrillion miles, a number so large that it loses meaning the moment it leaves your tongue. Yet here we are, tiny specks of consciousness inside this rotating storm of stars, orbiting something enormous and unseen at the center. If you look carefully, you notice something odd about the Milky Way's shape. It's not quite the perfect spiral you might expect, not a simple whirlpool of stars around a central bulge. Instead, there's a bright, elongated structure crossing its heart, a bar, a bridge of hundreds of billions of stars, stretching roughly 27,000 light-years from end to end, angled about 27 degrees relative to our line of sight. It's as if the galaxy's core had grown an axis, a glowing rod of light and gravity, through which everything else revolves. This isn't unique to us. 2/3 of all spiral galaxies we've observed in the universe are barred spirals. Some are subtle, some like NGC 1300 or NGC 1365 flaunt their bars like cosmic signatures dazzling across tens of thousands of light years. But we didn't always know our own galaxy had one. For most of human history, we thought the Milky Way was a smooth, circular disk with a spherical bulge, a kind of gentle celestial whirlpool, symmetrical and serene. The truth turned out to be stranger, more dynamic, and far more alive. So tonight, we're travelling inward, toward that heart, toward the glowing bar at the centre of our galaxy. It's a place we cannot see with our eyes, because between us and it lies a veil of interstellar dust, thick enough to block visible light completely. If you tried to look straight through it, you'd be staring into a dark, featureless patch of sky, right in the direction of the constellation Sagittarius. And yet, hidden behind that darkness, lies one of the most extraordinary regions in the universe, a vast, radiant bar of stars, gas, and dust, rotating around a supermassive black hole 4 million times the mass of our Sun. That's the enigma we'll explore. How do we know what lies at the galaxy's heart if we can't see it directly? How can we map a structure from within it, like trying to describe an entire forest while standing between the trees? And what does that bar actually do? Is it just decoration, or is it something deeper, a kind of gravitational heartbeat that helps the galaxy live, breathe, and evolve? To answer that, we have to start from a very human place, our own perception of the night sky. For thousands of years, people looked up and saw the Milky Way as a pale river of light flowing across the heavens. The ancient Greeks thought it was the spilled milk of the goddess Hera, Galaxias Kyklos, the Milky Circle. The Chinese called it the Silver River. The Inca saw it as a celestial reflection of the Urubamba, the great river that winds through Peru. And yet, for all that poetry, no one truly knew what it was made of. It wasn't until the early 17th century, when Galileo Galilei turned his telescope toward the sky, that the truth began to reveal itself. In 1610, he wrote that the Milky Way was a congeries of innumerable stars, packed so tightly that they blurred into a continuous glow. But even Galileo couldn't see the whole picture. He saw through the dust only partially, his optical telescope limited to visible light. The rest of the galaxy was hidden behind thick curtains of interstellar soot. It would take centuries and the invention of entirely new kinds of telescopes to peer through that darkness. By the late 19th century, astronomers like William Herschel and later Jacobus Kapteyn tried to map the Milky Way's structure by counting stars. They thought the Sun was near the centre, a perfectly human mistake. We tend to imagine ourselves at the heart of things, but as the 20th century dawned, new observations changed that view. In 1918, Harlow Shapley used variable stars called Cepheids to measure distances, realizing the Milky Way was much larger than anyone had guessed, about 100,000 light-years wide, and that the Sun was far from its centre. We live, it turned out, on the quiet outskirts, roughly 26,000 light-years away from the galactic core. Still, the question of what lay at that centre lingered. We couldn't see it. Visible light, blocked by dust, told us nothing. But radio waves could pass through, and in the mid-20th century, that changed everything. In 1951, astronomers Harold Ewan and Edward Purcell detected the faint 21-centimetre emission line of neutral hydrogen. Soon, radio astronomers were using this line to map our galaxy from the inside out, revealing its spiral arms, its gas clouds, and the first hints of its complex core. By the 1970s and 1980s, infrared and radio surveys began to suggest something unexpected. The stars at the centre weren't arranged in a perfect sphere or smooth disk. They formed a kind of elongated bar, extending through the core and tilting slightly relative to our viewpoint. It was as if the Milky Way's heart wasn't round at all, but stretched, elongated, alive with motion, and that realization changed how we understood the entire structure of spiral galaxies. So, what exactly is a galactic bar? Imagine the Milky Way as a cosmic whirlpool, a rotating disk of hundreds of billions of stars orbiting the centre under the influence of gravity. Now imagine that the gravitational field at the centre isn't perfectly circular, but slightly distorted. Over time, the stars respond to that distortion, forming elongated orbits that reinforce one another, like dancers aligning their steps in rhythm. The result is a self-sustaining bar, a dense, linear structure of stars and interstellar gas that rotates as a single unit within the galaxy. In scientific terms, it's called a non-axisymmetric gravitational potential. In simpler words, the galaxy isn't perfectly balanced, and that imbalance creates beauty. The bar acts like a cosmic engine. It channels gas from the outer disk inward, feeding new star formation and perhaps the supermassive black hole itself. It redistributes angular momentum, the rotational energy of the galaxy, helping stars migrate across vast distances over billions of years. If you could somehow hover above the Milky Way and watch it in time-lapse over a few 100 million years, you'd see the bar as a glowing spine twisting slowly, shepherding gas and stars toward the centre like a gravitational conveyor belt. And here's the astonishing part. The bar itself may not be permanent. Astronomers think it might have formed only a few billion years ago and could one day fade or dissolve, reshaping the galaxy once again. To understand this, we look outward to other galaxies that serve as mirrors of our own. The barred spiral galaxy, NGC 1300 61 million light-years away, looks almost like a textbook diagram, its bright bar cutting through the centre, arms curling outward like ribbons of starlight. NGC 1365, a giant about 56 million light-years distant, shows a bar nearly 100,000 light-years long. Through these examples, we learn what we cannot see directly in ourselves. By studying others, we glimpse our own reflection. Still, you might wonder, why can't we just photograph the Milky Way's bar directly? After all, we've taken images of distant galaxies billions of light-years away. The problem isn't distance, it's perspective. We're inside the Milky Way, buried in its disk, surrounded by dense clouds of gas and dust that absorb visible light. It's like trying to take a panoramic photo of a forest while standing deep among the trees. The light from the galactic centre in visible wavelengths simply never reaches us. Infrared light, however, can. In the 1990s, NASA's COBE satellite, the Cosmic Background Explorer, gave us the first real infrared maps of the Milky Way. It showed an unmistakable bulge with an elongated shape, the first strong evidence of a bar. Then came two MASS, the 2-micron all-sky survey, in 1997, and later Spitzer in 2003, which revealed an even clearer picture. They showed that the Milky Way's central bulge isn't symmetrical. It's shaped like a peanut or an X, a hallmark of barred spirals seen edge-on. Newer surveys, such as VVVV, Vista variables in the Via Lactea, and ESA's Gaia mission, have since refined this view with precise 3D mapping of millions of stars. According to these measurements, the Milky Way's bar stretches roughly 27,000 light-years, about 2.5 times 10 to the 17th kilometers, or 160 quadrillion miles. Its stars orbit the galactic center at speeds of up to 200 kilometers per second, around 450,000 miles per hour. And it's tilted about 27 degrees relative to the sun's position, meaning that from our perspective, one end of the bar lies closer to us, toward the constellation Scutum, while the other extends away towards Centaurus. These aren't just abstract statistics, they're a portrait of motion. Every star in that bar is part of a vast, slow dance around a black hole whose gravity holds the galaxy together. It's a structure we can't see, but we can feel through its influence, in the way stars move, in the way radio waves bend, in the slow breathing of the galaxy itself. And at the very core, beneath all that starlight, lies something even stranger, Sagittarius A star. A name that sounds like a catalogue entry but hides one of the most fascinating objects in the known universe. It's a point so small and so dense that millions of suns could vanish inside it without leaving a trace. A supermassive black hole about 4.3 million solar masses in size. It sits roughly 26,000 light-years from Earth in the direction of the Sagittarius constellation, near the border of Scorpius and Ophiuchus. When astronomers first detected a strong radio source there in 1951, they had no idea what it was. Only decades later, by watching the orbits of nearby stars, did they realize that something invisible yet incredibly massive was exerting a gravitational pull on everything around it. In 2022, the Event Horizon Telescope released the first direct image of Sagittarius A star, a glowing ring of light around a shadow, distorted by gravity itself. It confirmed what physicists had long suspected. At the center of our galaxy is a black hole, quietly shaping the dance of stars across hundreds of billions of kilometers. And that black hole, along with the bar that funnels matter toward it, defines the heartbeat of the Milky Way. So the next time you look up at the sky and see that faint white band stretching from horizon to horizon, remember, you're not just looking at stars, you're looking edge-on into the disk of a barred spiral galaxy, and somewhere, behind billions of light-years of dust, behind countless stars, behind the reach of our eyes, lies the bar, glowing softly in infrared, invisible yet essential. It's the galaxy's spine, its axis, its quiet, rotating heart, and through its gravity, through its long, slow rhythm, everything, including us, finds its place in motion. In this episode, we'll travel deeper into that heart. We'll explore how astronomers learned to map it, how the bar moves and breathes, and what happens near the event horizon of the black hole at its core. We'll see how light bends, how stars race, and how something that looks so serene from afar can be so turbulent up close. Because understanding the galaxy's center isn't just about astronomy, it's about perspective. It reminds us that even in something as vast as the Milky Way, structure emerges from chaos, and order from imbalance. That even the universe's calmest patterns are born from motion, tension, and time. And perhaps that's what the bar really is, not just a feature of the galaxy, but a symbol of its life. A line of light running through the dark, connecting everything that orbits around it. A reminder that at the heart of even the most chaotic systems, there's often something quietly holding it all together. So, if you're ready, let's begin the journey inward, toward the center, toward the bar at the galaxy's heart. Picture the Milky Way again, not as a grand spiral floating serenely in the void, but as we truly see it from our small home within. A flat band of light stretched across the night sky, glowing faintly against the dark. It's an ancient sight. Every civilization that has ever looked up has seen that same pale river of stars, a silver mist threading through constellations, fading softly toward the horizon. But for all its beauty, the Milky Way has always hidden its shape from us. We live inside it, deep within one of its spiral arms, surrounded by billions of stars and thick clouds of interstellar dust. Trying to map it from here is like trying to draw the outline of an ocean while standing waist-deep in its waves. Our view is blocked, distorted, and limited by the very thing we are trying to understand. Even light itself struggles to cross that distance. Dust particles only a few micrometers wide scatter and absorb visible light, especially the bluer wavelengths. By the time a beam of starlight travels a few thousand light-years through the galactic plane, it's dimmed and reddened beyond recognition. If you could somehow remove all the dust, the night sky would blaze with countless stars, 10 times brighter than what we see. But with that dust in place, our galaxy becomes a puzzle viewed through a fog. This was the challenge faced by astronomers for most of human history. They could see the Milky Way, but not what it was. They could not step outside to look back and trace its arms. They had to deduce its shape from within, one faint clue at a time. In the 18th century, William Herschel, who built his own telescopes and catalogued thousands of stars, attempted one of the first maps of the Milky Way. He reasoned that by counting how many stars appeared in different directions, he could infer the shape of the system we lived in. In 1785, Herschel published a sketch, a kind of lopsided, star-filled disk, thicker in the middle and thinner at the edges, with the sun placed right at its centre. It was a reasonable guess, given what he could see, but it was also wrong, beautifully, humanly wrong. The clouds of dust between the stars fooled him, hiding vast regions of the galaxy and making the sun's neighbourhood appear like the middle of everything. A century later, astronomers were still struggling with the same illusion. In 1904, Dutch astronomer Jacobus Kapteyn used star counts and proper motions, the tiny shifts of stars across the sky, to refine Herschel's idea. He imagined the Milky Way as a flattened, lens-shaped island of stars, about 17,000 light-years across and 3,000 light-years thick, again with the sun near the centre. The Kapteyn universe, as it was called, was elegant, mathematical, and entirely self-contained, and, as we later discovered, just as wrong as Herschel's. It wasn't that Kapteyn made mistakes in arithmetic, he simply couldn't see far enough. The dust in the galactic plane acted like a curtain, blocking most of the light from the core, so his universe was only a small, dimly lit patch of the real one. It would take the work of Harlow Shapley in 1918 to break that illusion. By studying Cepheid variable stars, stars that pulse in brightness at rates directly related to their true luminosity, Shapley could estimate distances much more accurately. He noticed that clusters of these stars, called globular clusters, were not scattered evenly across the sky. Instead, they formed a broad, asymmetrical swarm concentrated toward the constellation Sagittarius. From that, Shapley deduced that the true centre of the Milky Way lay far beyond the Sun, roughly 26,000 light-years away, in that same dusty direction. It was a revolutionary realization. We were not at the centre of our galaxy. The universe once again had politely moved us aside. Still, knowing where the centre was didn't mean we could see it. For decades afterward, astronomers were trapped by the limitations of visible light. They could measure positions of stars and nebulae, but not the grand structure connecting them. The Milky Way's spiral arms, if they existed, were invisible from our dusty vantage point. The best diagrams of the mid-20th century looked more like imaginative sketches than maps filled with question marks and cautious curves. Then, in the early 1950s, a quiet revolution began, one that didn't use light at all. A new kind of astronomy had arrived, radio astronomy. Unlike visible light, radio waves can pass straight through the clouds of dust that obscure the galactic centre. And among all radio signals, one frequency turned out to be the key to unlocking the Milky Way's shape, the 21-centimetre line of neutral hydrogen. Every hydrogen atom in the universe can, very occasionally, flip the orientation of its single electron relative to its proton. When that happens, it emits a photon, a packet of energy. corresponding to a wavelength of 21 centimeters, or a frequency of about 1420 megahertz. It's a rare event for any individual atom, but because hydrogen is by far the most abundant element in the cosmos, the combined signal is immense. By detecting this emission, astronomers could suddenly see the structure of the galaxy, not in visible light, but in radio. In 1951, American physicists Harold Ewan and Edward Purcell at Harvard detected the 21-centimeter line for the first time. Within months, observatories around the world built their own antennas to listen for it in the Netherlands, Australia, South Africa, and the United States. By measuring slight shifts in the frequency of that hydrogen emission caused by the Doppler effect as clouds of gas move toward or away from Earth, astronomers could calculate their velocities and positions relative to the galactic center. For the first time in history, we could map the Milky Way from the inside. We couldn't see the stars, but we could hear the gas that surrounded them. By 1958, teams had pieced together the first radio map of our galaxy, showing a distinct spiral pattern, vast arms curving around the center like the swirls of a hurricane. It was an astonishing confirmation that the Milky Way really was a spiral galaxy, much like Andromeda or the great galaxies seen in deep space photographs. We finally knew our cosmic home was not an amorphous cloud, but a structured, rotating disk. But even with this new insight, the view was still incomplete. Hydrogen gas traced the broad outlines of the arms, but it didn't reveal everything. The inner regions, the dense, crowded core, remained confusing, full of overlapping signals and strange motions. The heart of the Milky Way was still a riddle. In the 1960s and 1970s, astronomers began combining radio data with infrared observations. Infrared light can also penetrate dust, though not as easily as radio waves, and it reveals the glow of stars themselves rather than the cold gas between them. With this new window, they could begin to map the bulge, the dense spherical region of older stars near the galactic center. What they found was unexpected. The brightness of the bulge wasn't symmetrical. It was brighter on one side than the other, as though the entire central region was tilted relative to the rest of the disk. Something didn't add up. By the late 1970s, researchers like Paul Schechter, Alistair Walker and Leo Blitz were proposing that the inner galaxy might not be a simple sphere at all, but an elongated structure, a bar of stars stretching across the core. Observations of gas motions backed them up. Instead of orbiting smoothly in circles, clouds of hydrogen and carbon monoxide near the center moved along oddly elliptical paths consistent with the gravitational influence of a bar. In the decades that followed, this idea gathered strength. Infrared surveys with the Infrared Astronomical Satellite, IRAS, in 1983, and later the COBE mission in 1990, revealed more and more evidence of a bar-shaped bulge. COBE's data, released in 1991, showed that the Milky Way's central region was indeed elongated, roughly 27,000 light-years long and angled relative to our line of sight. It was a turning point. For the first time, we knew that our galaxy was not a simple spiral, but a barred spiral, part of the majority class of spirals we see across the universe. Yet, even now, mapping the Milky Way is a feat of patience and imagination. When you look out across the night sky, you're not just seeing stars at different positions, you're seeing stars at different times. Light takes tens of thousands of years to reach us from the far side of the galaxy. Every photograph of the Milky Way is a mosaic stitched together from ancient light, filtered through dust, distorted by gas, and blurred by our own movement around the center. Astronomers rely on ingenious methods to turn this chaos into a coherent model. They combine parallax measurements, tiny shifts in a star's apparent position as Earth moves around the Sun, with Doppler velocities, infrared brightness, and statistical modeling. They simulate how stars orbit within the galactic gravitational field and compare those models with what we observe. The process is a blend of data and deduction, of mathematics and art. The Gaia spacecraft, launched by the European Space Agency in 2013, has pushed this to a new level. By measuring the positions and motions of more than 1.8 billion stars with astonishing precision, some to within a few dozen micro-arc seconds, Gaia has created the most detailed 3D map of our galaxy ever assembled. From this mountain of data, astronomers can see the faint warp of the Milky Way's disk, the ripples caused by past galactic collisions, and the subtle streaming motions of stars that betray the presence of the central bar. Even though we can't fly above the galaxy to photograph it, we now understand its structure in remarkable detail. We know it has at least 4 major spiral arms: the Perseus arm, the Scutum Centaurus arm, the Sagittarius arm, and the outer arm, along with numerous spurs and bridges. We know our Sun sits in a minor spur called the Orion arm, roughly halfway between the centre and the outer edge. And we know that all of these arms, all of these stars, orbit around a massive, invisible core roughly every 230 million years, the time it takes for one full galactic year. From a human perspective, that's almost impossible to grasp. Every time the Sun completes a single orbit around the centre, life on Earth has evolved dramatically. When the dinosaurs walked the planet, we were in a completely different part of the galaxy. When the first mammals appeared, the Sun was already well along its current galactic path. In the time since humans first made tools, our solar system has moved less than 1,000th of a full orbit, just a few dozen light years through the disk. So when we talk about the bar at the galaxy's heart, we're talking about something almost timeless on the human scale, a structure that has existed for billions of years, guiding the flow of matter through the Milky Way, while entire species, continents, and civilizations rise and vanish on a single tiny planet within it. What's remarkable is how much of this picture we've built without ever stepping outside. We're still the observers inside the forest, but the fog has lifted enough to glimpse its shape. We've learned to use every wavelength of the electromagnetic spectrum like a different kind of vision. Radio, to hear the hydrogen clouds, infrared to see through the dust, visible light for the nearby stars, ultraviolet and X-rays for the hottest, most energetic regions. Each piece adds another layer to the portrait, and though we still cannot see the Milky Way's bar directly with our eyes, we can trace its presence in the motions of stars, in the symmetry of the bulge, in the way the inner gas streams bend and twist under gravity. It's a detective story told through physics and patience, the art of mapping something from within by listening to its echoes. Sometimes it's easy to forget how young this knowledge really is. Less than a century ago, we didn't even know the Milky Way was just one galaxy among billions. In 1920, the famous Great Debate between Harlow Shapley and Heber Curtis still questioned whether the spiral nebulae seen in the sky were distant galaxies or nearby clouds of gas within our own. The idea that the universe was filled with countless other galaxies, many of them barred like ours, wasn't confirmed until Edwin Hubble's observations of Cepheid variables in Andromeda in 1923. From that moment to now, just 100 years have passed, a cosmic blink, and yet we've gone from star counts and sketches to 3D digital atlases of billions of stars. We've gone from thinking we lived at the centre of a small cluster to realising we orbit a supermassive black hole in a barred spiral galaxy that's part of a web of hundreds of billions of others. When you step outside tonight and see that soft streak of light cutting through the darkness, you're looking through time and dust at a structure we've only recently begun to understand. Each faint shimmer is a data point, a clue, part of a map drawn by minds that refuse to accept darkness as a boundary. We are creatures who insist on knowing where we are, even if it means listening to the faint whisper of hydrogen across 100,000 light years of space. That whisper told us our galaxy has arms. Infrared light revealed it has a bar, and gravity, invisible, relentless, told us what lies at its heart. But to understand why that heart exists, why galaxies grow bars at all, and what that means for the fate of the Milky Way, we have to look deeper still, into the strange physics of rotating stars and self-organizing chaos. Because the bar at the galaxy's heart isn't just a shape, it's a process, a cosmic rhythm that may define how galaxies live and die. And that's where our journey leads next. If you could hover high above the Milky Way, far beyond its spiral arms, looking down from the cold stillness of intergalactic space, you would see a sight both familiar and alien. A glowing disk of light, dust lanes curling outward in sweeping arms, and at its centre, something unexpected. Not a simple round hub, but an elongated band of brightness, a luminous bar running through the middle like the handle of a celestial pinwheel. That bar isn't an illusion, it's real, a structure of staggering scale and complexity, tens of thousands of light years long, packed with stars, gas, and molecular clouds. It rotates slowly, majestically around the galaxy's core, and everything else moves in response to its gravity. It's not merely a decoration, not a scar or an accident of cosmic geometry. It's an engine, a living part of the Milky Way's machinery, shaping how stars are born, how they drift, and how our galaxy evolves across billions of years. So what exactly is a galactic bar? At first glance, it looks like a bridge of stars, an elongated bulge running through the galactic center. But the bar isn't a rigid structure like a metal beam. It's made of millions upon millions of stars, each moving in its own orbit, bound together only by gravity. The bar we see is really a pattern, a collective behavior, like the arms of a spiral galaxy or the crest of a wave in the ocean. The wave moves, but the water doesn't travel with it. In the same way, the bar is a pattern in motion. Stars flow through it, drift out, and new ones take their place, all the while maintaining the bar's shape. If we could watch the Milky Way in time-lapse over hundreds of millions of years, we'd see the bar rotating as a unit, completing a full turn roughly every 100 to 150 million years. That means the bar rotates 2 or 3 times for every one complete orbit the Sun makes around the galaxy. From our position in the disk, the effect is subtle, invisible, but on the grand scale, it sculpts the entire flow of the Milky Way's matter. In astronomical terms, the bar is said to be a non-axisymmetric gravitational potential. That phrase may sound dry, but it hides something profound. It means the galaxy's gravity isn't perfectly balanced around the center. Instead of being circular and uniform, the gravitational field is slightly lopsided, denser along the bar's length. Stars and gas clouds moving through this uneven field are tugged into elongated orbits, reinforcing the shape of the bar and keeping it stable. It's a kind of self-organization on a cosmic scale, gravity turning chaos into order, imbalance into structure. To understand how such a thing can exist, we have to talk about orbital resonances, the secret rhythm inside every rotating galaxy. Imagine billions of stars orbiting the galactic center. Each one moves under the combined gravity of all the others, tracing out an ellipse that precesses or slowly rotates over time. Now imagine that some of those stars happen to orbit in sync with a certain pattern speed, the rotational speed of the bar itself. When that happens, their orbits line up in such a way that they reinforce the bar's gravitational field instead of disrupting it. They get locked into resonance. Think of a swing being pushed at just the right moment, again and again. Each push adds a little energy, amplifying the motion. In the same way, the gravitational tugs from the collective motion of the bar keep certain stellar orbits aligned, sustaining the overall shape. This is the essence of a galactic bar, a vast resonance, a harmonic structure formed by gravity's music. The stars within the bar don't follow simple circular paths. Their orbits are elongated, oriented roughly along the bar's major axis. Some loop in figure-8 shapes, others trace more complex curves, but together they create a coherent flow, a gravitational dance where individual motions build a collective whole. This alignment can arise spontaneously. Computer simulations have shown that even a perfectly round, rotating disk of stars is unstable over long periods. Small irregularities, random density fluctuations grow over time. As they do, they create slight asymmetries in the gravitational field, which in turn pulls stars into more elongated orbits. Within a few 100 million years, a disk can develop a distinct bar all on its own. The process is so common that most spiral galaxies in the universe end up with one at some stage of their evolution. Bars don't just look impressive, they do things. They are engines of motion and change. When a bar forms, it begins to redistribute angular momentum, the rotational energy of the galaxy. Gas and stars in the outer regions lose energy and move outward, while material closer to the center gains energy and moves inward. The bar acts as a conveyor belt, funneling interstellar gas toward the core. That flow of gas has enormous consequences. As clouds spiral inward, they collide, compress, and ignite new waves of star formation. The central regions of barred galaxies often glow with young, hot, massive stars, stellar nurseries powered by the bar's gravitational pull. Some of that infalling gas even feeds the central black hole, providing the material for energetic outbursts and jets in active galaxies. In this sense, the bar literally fuels the heart of the galaxy, both figuratively and physically. The process happens slowly, over tens or hundreds of millions of years, but on cosmic timescales, it reshapes the entire structure. A galaxy without a bar tends to be more quiescent. Its gas spread evenly across the disk. A barred galaxy, by contrast, is dynamic and evolving, constantly redistributing its contents, triggering bursts of activity near its core. The Milky Way's bar performs exactly this role. Our galaxy's central molecular zone, the dense region of gas and dust within about 1,500 light-years of the centre, is fed by streams of material channeled inward along the bar. These streams twist into giant ring-shaped structures near the core, where conditions for star formation are extreme. Gas densities thousands of times higher than in the solar neighbourhood, temperatures of tens to hundreds of kelvins, around -200 degrees Celsius to -70 degrees Celsius, or -330 degrees Fahrenheit to -90 degrees Fahrenheit, and pressures billions of times greater than those inside Earth's atmosphere. It's a place where stars are born in clusters, often forming massive, short-lived giants that explode as supernovae only a few million years later. Each explosion stirs the region again, pushing gas outward, feeding turbulence, and sustaining a cycle that can last for eons. Without the bar, much of that gas might remain in the outer disk, forming stars more slowly and inefficiently. The Milky Way would be quieter, perhaps even less structured. In a strange way, the bar gives our galaxy its vitality, the slow heartbeat that pumps matter toward its luminous centre. The physics behind this is subtle but beautiful. In a rotating galaxy, everything balances between gravity and motion. Gravity pulls inward, while the centrifugal effect of rotation pushes outward. In a perfectly circular system, those forces remain stable, and material orbits smoothly around the centre. But introduce a small distortion, an uneven distribution of mass, and the symmetry breaks. Some regions pull a little harder, others lag behind. Stars begin to bunch up along certain directions, reinforcing the unevenness. Soon a bar forms, and with it, a network of resonances that redistribute angular momentum throughout the disk. This redistribution can cause stars to migrate vast distances over their lifetimes, a process known as radial migration. A star born in one part of the galaxy can, through interactions with the bar and the spiral arms, drift thousands of light years inward or outward. In fact, some of the stars near our Sun today may have originated closer to the galactic centre, while others were born farther out and moved inward. Over billions of years, this slow stirring mixes the galactic disk like a vast cosmic soup, blending populations of stars of different ages and chemical compositions. You could think of the bar as the galaxy's mixing spoon, a gravitational mechanism that churns the stars, ensuring that the Milky Way never grows stagnant. This mixing affects not only where stars end up, but also how heavy elements, the oxygen, carbon, and iron forged in stellar cores, are distributed. As stars live, die, and scatter their contents, the bar helps spread those elements across the galaxy, enriching the interstellar medium that will one day form new generations of stars and planets. Without that process, the Milky Way might be a patchwork of isolated zones, metal rich near the centre, metal poor on the edges. Instead, thanks in part to the bar, it's a gradient, smooth, connected, alive. In the 1990s, numerical simulations began to reveal how complex and self-regulating this process really is. When astrophysicists modelled disk galaxies with millions of particles, stars, gas, dark matter, they found that bars form naturally under a wide range of conditions. But they don't always last forever. Over time, as the bar drives gas inward, the central mass concentration increases. That extra mass can eventually weaken the bar's gravitational coherence, causing it to fade or even dissolve. Later, as the disk stabilizes and new asymmetries arise, a new bar can form, and the cycle begins again. Some galaxies may go through several bar phases over their lifetimes, each lasting a few billion years. In the Milky Way's case, evidence suggests our current bar may have formed between 5 and 8 billion years ago, though its precise age is still debated. That means it's roughly half as old as the galaxy itself, old enough to have shaped much of what we see today, but young enough that it's still evolving. Observations from the Gaia mission show subtle signs of ongoing change, patterns in stellar motions, slight ripples in the disk, perhaps hints of a secondary inner bar, a smaller structure nested within the larger one. The Milky Way, it seems, is still settling into its latest rhythm. The question of why galaxies grow bars in the first place touches on some of the deepest mysteries of galactic evolution. In essence, a bar is a natural response to instability. When a disk of stars rotates too quickly or becomes too massive, tiny fluctuations can no longer be smoothed out. Instead, they amplify like ripples becoming waves. Gravity magnifies any slight overdensity, pulling more material into the same region until a coherent, elongated shape emerges. This process depends on several factors: the mass of the disk relative to its dark matter halo, the speed of rotation, the distribution of stars, and the amount of gas. Galaxies with more massive, faster rotating disks tend to form bars more easily. Bars may also emerge during galactic interactions, close passes or minor collisions with neighbouring galaxies that disturb the symmetry of the disk. In that sense, a bar can be both a natural outcome of internal physics and a scar left by encounters with the cosmos. Either way, once a bar forms, it transforms the galaxy's destiny. It alters the pattern of spiral arms, the flow of gas, the rate of star formation. Even the shape of the central bulge, that bright swollen region of old stars, can be reshaped by the bar's gravitational influence. The Milky Way's X-shaped bulge, revealed in infrared light, is likely the direct result of stars trapped in the bar's resonant orbits, lifted above and below the plane of the disk over billions of years. From a poetic point of view, it's astonishing to think that something as intangible as an imbalance in gravity can sculpt a galaxy. The bar is not an object, but a pattern, a standing wave of motion millions of light years across, and yet that pattern governs the flow of matter and energy on a scale we can barely imagine. It's as if the universe itself discovered harmony, a balance between chaos and order, and built it into the architecture of galaxies. When you look at images of distant barred spirals, each one tens or hundreds of millions of light years away, you're seeing echoes of the same physics that shapes our own Milky Way. Every one of those glowing bars is a bridge between motion and stillness, a gravitational chord struck in the cosmic symphony. And just as in music, the pattern depends on resonance, timing, and feedback, the subtle exchange of energy that keeps everything in tune. If we could hear the Milky Way instead of see it, the bar might sound like a deep, slow pulse, a bass note in the soundtrack of the cosmos. It beats once every 100 million years or so, stirring the stars, moving gas toward the centre, feeding creation and destruction in equal measure. Through it, the galaxy breathes, expanding, contracting, rotating endlessly. And we, orbiting quietly far from that centre, are part of its rhythm. Our solar system drifts through the outer disk, tracing its own slow spiral, never noticing the grand mechanism guiding it all. Yet every atom in our bodies, every molecule of oxygen and iron, was once part of that cosmic cycle, forged in stars whose formation may have been triggered by the bar's gravitational pull billions of years ago. So when we talk about the shape of a bar, we're not describing something distant and abstract. We're describing a process that helped make us, a pattern that links the heart of the galaxy to the chemistry of life on a small blue world orbiting an average star. The Milky Way's bar reminds us that imperfection breeds beauty, and a perfectly symmetrical galaxy might be stable, but lifeless. It's the imbalance, the distortion, the tiny deviation from perfection that gives rise to complexity, motion, and change. From that slight asymmetry comes the pulse that drives stars to form, die, and form again. Gravity doesn't just pull things together, it creates stories, and the bar at the galaxy's heart is one of its longest-running tales. A story of instability turned into order, of chaos reshaped into rhythm. A story still unfolding, one slow rotation at a time. For most of human history, the center of our galaxy was hidden from us, a place of mystery, veiled behind curtains of cosmic dust. We looked toward the constellation Sagittarius and saw only a faint patch of stars, dimmed and reddened by interstellar soot. We could point to where we thought the galactic core should be, but beyond that, nothing. Just darkness. Then, in the closing years of the 20th century, we learned a new way to see. We began to look not with our eyes, but with light that our eyes could never detect, light with wavelengths long enough to slip through the dust unimpeded. It was a shift as revolutionary as Galileo's first telescope. This time, instead of polishing glass, we built machines that could see in infrared. Infrared astronomy changed everything. It allowed us to see through the Milky Way's fog, to look into the crowded, glowing heart of the galaxy itself. And what we found there was nothing like the smooth, round bulge we once imagined. It was complex, asymmetric, almost architectural, a tilted bar of stars crossing the core, and within it an elegant, faintly glowing X, a shape written not in myth, but in light. To understand how we came to see it, we need to go back to the early 1990s, a time when space telescopes were still a daring idea, and the world was only beginning to glimpse the universe beyond visible light. On November 18, 1989, NASA launched a small, boxy satellite into orbit, not to take pretty pictures, but to measure the faint glow of the cosmos itself. It was called COBE, short for Cosmic Background Explorer. Its main mission was to study the relic radiation left over from the Big Bang, but one of its instruments, the Diffuse Infrared Background Experiment, or DIRBE, had another goal: to map the entire sky in infrared light. For the first time, astronomers could observe the Milky Way in wavelengths that sliced through the dust. Derby's detectors scanned the sky for nearly a year, collecting data at 10 different infrared bands, from 1 to 240 micrometers, far beyond the range of human vision. When the first images came in, they were startling. The galactic plane, invisible light, blazed with infrared emission. Cold dust clouds glowed faintly. Regions that had once been blank became filled with structure, and right in the middle, the bulge of the Milky Way revealed a secret. It wasn't round. It was stretched, skewed, brighter on one side than the other. The light distribution formed a faint diagonal, suggesting that the central mass of stars wasn't symmetrical at all, but tilted, elongated along a bar. For decades there had been hints of such a shape, inferred from radio and optical data, but this was the first time humanity saw it. The Milky Way was a barred spiral galaxy, and the bar wasn't straight toward us. It was angled roughly 27 degrees from the line connecting the Sun to the galactic center. One end of the bar extended closer to us, toward the constellations Scutum and Norma, while the other stretched away toward Centaurus. The symmetry of the universe had tilted ever so slightly, and it changed how we saw everything. The COBE discovery was more than a curiosity. It was a revelation of structure. Astronomers began to model the central region in 3 dimensions, using the intensity of infrared light as a proxy for the number of stars along each line of sight. By deprojecting the data, essentially unfolding the 2D image into a 3D map, they revealed the geometry of the Milky Way's bulge, elongated, triaxial, and rotating. It wasn't a simple sphere, but a peanut-shaped, even X-shaped region, the result of stars caught in resonant orbits around the galactic bar. That shape, faintly glowing in infrared, became one of the defining features of our galaxy. It told us that the Milky Way wasn't static or symmetrical, it was dynamic and alive, a system in constant motion. But COBE, as powerful as it was, had a limited resolution. Its detectors were coarse, its pixels large, enough to see broad patterns, but not the fine details. To truly trace the bar, astronomers would need sharper eyes. In the late 1990s, those eyes arrived. The 2-micron All-Sky Survey, or 2MASS, launched in 1997 as a collaboration between the University of Massachusetts and the Infrared Processing and Analysis Center at Caltech. Unlike COBE, 2MASS used ground-based telescopes, one in Arizona, one in Chile, equipped with highly sensitive infrared detectors. Over 4 years, it scanned the entire sky in 3 near-infrared bands, at wavelengths of 1.25, 1.65, and 2.17 micrometers, cataloguing nearly 500 million stars. Each one of those stars became a data point, a marker in the great map of the Milky Way. The dust that once hid the galactic center was now transparent, at least partially. Through it, astronomers could see the density of stars rising sharply toward the middle, then stretching into that now familiar elongated shape. The bulge was not only barred, it had a distinctive X-shaped structure formed by stars orbiting in figure-8 paths around the galactic core. This discovery carried profound implications. The X-shaped bulge wasn't an exotic feature, it was the natural consequence of a bar viewed edge-on. As the bar rotates, some stars are trapped in resonant orbits that lift them above and below the galactic plane, forming the 2 arms of the X. It's a purely dynamical phenomenon, gravity and motion sculpting stars into geometry. In that shape, the Milky Way revealed both its structure and its history. Around the same time, another spacecraft was preparing to take the next leap. In 2003, NASA launched the Spitzer Space Telescope, designed specifically for infrared observation. Spitzer carried a large 85-centimeter mirror and 3 sensitive instruments, all cooled to just a few degrees above absolute zero, around minus 270 degrees Celsius or minus 454 degrees Fahrenheit, to minimize its own heat emissions. For more than 16 years, until it was retired in 2020, Spitzer mapped the universe in exquisite infrared detail. For the Milky Way, Spitzer's contribution was transformative. Its glimpse, Galactic Legacy Infrared Mid-Plane Survey Extraordinaire program, scanned the entire galactic plane, producing images of unprecedented clarity. Where COBE had shown a smudge and 2MASS had shown points, Spitzer showed a structure, a glowing band of stars stretching across the galactic center, surrounded by filigrees of dust and gas. The bar's full shape came into focus, roughly 27,000 light-years long, with its nearer end just 5,000 light-years closer to us than its far side. It's astonishing to think that such a small difference in angle, just 27 degrees, could remain hidden for so long. From our position inside the disk, perspective disguises everything, but through infrared light, the illusion falls away. What once seemed like a featureless bulge becomes a living, 3-dimensional landscape. Each of these missions, COBE, 2MASS, and Spitzer, built on the last, deepening our vision of the galaxy. Together, they told a story of persistence, of human curiosity peeling back layer after layer of darkness until the invisible became visible. The discovery of the X-shaped bulge also changed how we interpret the Milky Way's past. It suggested that our galaxy's bar formed through secular evolution, slow internal processes rather than violent mergers. Over billions of years, the Milky Way's disk became unstable, the bar emerged, and stars near the center were gradually lifted into box-shaped orbits, forming the bulge we see today. It's a gentle form of self-sculpting, gravity reshaping itself from within. Other galaxies observed edge-on show the same structure, NGC 4565, NGC 5746, and countless others display that same elegant X. By studying them, we understand our own. The Milky Way is just one example in a vast family of barred spirals, all following the same physics. Each bar a signature of dynamical maturity, but the story doesn't end with Spitzer. Even sharper tools have emerged in the 21st century, bringing the galactic center into clearer focus than ever before. One of these is Gaia, launched by the European Space Agency in 2013. Gaia was not designed primarily for infrared observation. It works mostly in optical light. but its precision astrometry has revolutionized our understanding of the Milky Way's structure. By measuring the positions, distances, and motions of more than 1.8 billion stars, Gaia provided the raw data needed to model the galaxy in 3 dimensions. From Gaia's measurements, astronomers can see subtle streaming motions that betray the presence of the bar. Stars near the centre move in elliptical patterns aligned along that 27-degree tilt. Some are speeding up, others slowing down, depending on their position relative to the bar's rotation. It's like watching the gears of a vast, invisible machine turning in slow motion. When these kinematic maps are combined with infrared surveys like VVV, the VISTA variables in the Via Lactea project, conducted with the 4.1-meter VISTA telescope in Chile, the result is breathtaking. VVV operates in near-infrared light, mapping tens of millions of stars across the inner Milky Way with extraordinary depth. Its data reveal the bar's full shape, not just its length and angle, but its vertical structure. The X-shaped bulge rising thousands of light-years above and below the galactic plane. From these combined datasets, astronomers have reconstructed the most detailed 3D model of our galaxy's centre ever made. They can trace individual stellar populations, younger stars along the bar, older ones in the bulge, and even estimate the bar's rotation speed, about 40 to 55 kilometers per second per kiloparsec. Translated, that means stars near the centre complete 1 bar rotation roughly every 120 million years, a slow, steady rhythm that has pulsed since before the Earth formed. Looking at these images, false colour mosaics made from infrared data, is a strange experience. The galaxy's centre glows with gold and red, its dust lanes sweeping like brushstrokes of smoke. The X-shaped bulge stands out faintly, elegant and geometric, like the framework of a vast cosmic cathedral. It's hard not to feel a sense of awe, not only at the structure itself, but at the thought that it was invisible for so long. For millennia, humans stared towards Sagittarius and saw only emptiness. Now we know that beyond that darkness lies the luminous heart of our galaxy, a place of turbulence, birth, and motion. Infrared light, with its longer wavelengths, became the language through which we finally read that story. It's almost poetic. To understand the brightest region of the Milky Way, we had to use light too faint for our eyes to perceive. To reveal what was hidden, we had to step outside our own senses. Every improvement in our instruments has peeled away another layer of illusion. What began as a patch of sky became a map of light. What looked like a bulge became a bar. What seemed flat became a 3-dimensional structure, rotating and alive. Astronomy has always been an act of patience, of seeing what isn't yet visible. And nowhere is that patience more rewarding than here, in the centre of our own galaxy. Today, we can model the Milky Way's heart, not as a blur, but as a living system. We know its bar extends roughly 13,500 light-years in each direction from the centre. We know it's tilted about 27 degrees, and that the near side lies around 25,000 light-years from us. We know the bar's ends connect smoothly to the spiral arms, forming a continuous flow of stars and gas. And we know that the X-shaped bulge isn't an artifact. It's the 3-dimensional skeleton of that rotating structure, a fossil of the bar's long, slow evolution. It's remarkable. From the outside, the Milky Way would look like a glowing whirl of stars. But from within, we had to reconstruct that image piece by piece, using wavelengths invisible to our eyes and equations to fill in the missing depth. What once was guesswork has become geometry. The galaxy's heart has gone from mystery to map. And yet, even with all this clarity, there's still something elusive about the Milky Way's centre, something that resists being fully captured. The bar and its X-shaped bulge are not static. They shimmer, evolve, and breathe with time. Stars move in and out of the pattern. Gas flows inward, and the entire structure slowly twists as the galaxy rotates. Infrared light freezes a moment in that motion, but the real Milky Way is never still. It is a process, not a picture. Every photograph we take is a frame in a billion-year film. And what we see in those frames, the glowing bar, the X of light, the asymmetric heart, is a story still unfolding, a story of gravity sculpting beauty from chaos and of human vision finally catching up. The journey from COBE to Gaia is a journey from blindness to sight, from a vague glow to a three-dimensional understanding of where we live. It's the story of how we learned to look through the dust and see not just stars, but structure, order, motion, and history. Infrared light gave us that vision. It taught us that darkness is often just an illusion, and that beyond what we can see lies everything we could ever want to understand. The bar at the galaxy's heart was there all along, waiting for us to learn the right kind of sight. And now that we can finally see it, the next question is inevitable. What's happening there, in that luminous core, where gravity is strongest, where gas flows inward and stars race around an invisible centre at thousands of kilometres per second? To answer that, we'll have to go deeper still, into the very heart of darkness, where the Milky Way's brightest light begins to fade into the pull of its black hole. If the Milky Way has a heart, then Sagittarius A star is the pulse that never stops, a single, silent point at the galaxy's centre, invisible, yet so powerful that everything around it moves in response. For centuries, that heart was only a hypothesis, a blank spot in the sky. Then, piece by piece, we began to realise that at the centre of all the stars, behind the dust and the glare, lies a darkness so dense that even light cannot escape. The Milky Way, it turns out, is built around a supermassive black hole. The story began not with a photograph, but with a faint radio signal. In 1951, two American astronomers, Harold Ewan and Edward Purcell, famous for detecting the 21-centimetre hydrogen line, helped open the era of radio astronomy. That same year, at the US Naval Research Laboratory in Washington, D.C., Bruce Parnell and Harold "Doc" Brown turned their antenna toward the constellation Sagittarius, the direction of the galactic centre. What they found was a compact, unusually bright radio source. They called it Sagittarius A. It was just one of many sources in that direction, but its compactness made it special. Over the next 2 decades, as radio telescopes improved, astronomers kept returning to that patch of sky. In 1974, with the newly built Green Bank Interferometer in West Virginia, Bruce Ballick and Robert Brown discovered something extraordinary. Nested within Sagittarius A was a region so small and so intense in radio emission that it couldn't be an ordinary star cluster or supernova remnant. They named it Sagittarius A star, the asterisk meaning exciting source. That simple designation, a letter and a symbol, would come to represent one of the most fascinating objects in the universe. At first, few dared to suggest it was a black hole. The very term still carried controversy. Einstein himself had doubted that nature would allow such singularities to exist. But as observations improved through the 1970s and 1980s, evidence mounted. Sagittarius A star emitted strong radio waves, but almost no visible or ultraviolet light, meaning it wasn't composed of ordinary hot gas. It didn't move across the sky, implying it sat deep within the galactic centre, about 26,000 light-years away, roughly 250 trillion kilometres, or about 155 trillion miles. Yet its apparent size was astonishingly small. Interferometric observations showed it to be less than 1 astronomical unit wide, smaller than the orbit of Earth around the Sun. To pack millions of solar masses into such a tiny region would require densities beyond imagination. By the late 1980s, suspicion hardened into conviction. Something compact and incredibly massive lurked there, but no one could see it directly. And to prove its existence, astronomers would have to watch the stars that danced around it. In the early 1990s, 2 independent teams began a painstaking campaign that would last decades. At the W.M. Keck Observatory in Hawaii, Andrea Ghez and her colleagues used adaptive optics systems to counteract the blurring of Earth's atmosphere. Across the Atlantic, at the Very Large Telescope in Chile, Reinhard Genzel and his team at the Max Planck Institute for Extraterrestrial Physics did the same. Both groups targeted a tight cluster of stars only light days away from Sagittarius A star. These stars, now known as the S cluster, were moving at unimaginable speeds, some over 5,000 kilometers per second, or about 11 million miles per hour. By tracking their positions year after year, the teams could map their orbits with exquisite precision. One star in particular, known as S2, became the key. Roughly 15 times the mass of the Sun, it completes one orbit around Sagittarius A every 16 years, swooping as close as 17 light hours, about 120 astronomical units, or 18 billion kilometers, roughly 11 billion miles, from the center. At its nearest approach in 2018, S2 reached a velocity of nearly 8,000 kilometers per second, about 18 million miles per hour, or roughly 3% of the speed of light. From those orbits came the numbers that sealed the case. The mass required to keep S2 bound in its orbit was roughly 4.3 million times the mass of the Sun, all confined within a region smaller than our solar system. No cluster of normal stars, no swarm of dark stellar remnants could be that dense or stable. Only a black hole could fit the data. The teams continued observing, refining their models, and by 2020 their work was recognised with the Nobel Prize in Physics. Half went to Roger Penrose for proving that black holes are a direct consequence of general relativity. The other half to Andrea Ghez and Reinhard Genzel for confirming that a supermassive black hole sits at the centre of the Milky Way. For all the triumph of orbital measurements, one question lingered. Could we actually see it? Not the stars or the gas, but the black hole itself? In 2019, the Event Horizon Telescope, or EHT, answered that question for another galaxy. It released the first ever image of a black hole's shadow, the glowing ring around M87 star, a monster 6 billion solar masses in the Virgo cluster. That picture, a blurry orange halo surrounding darkness, became an icon overnight. But for astronomers, the real prize was closer to home. Sagittarius A. Imaging it would be far harder. M87's black hole is much larger, so its light-bending features change slowly. Sagittarius A*, smaller by a factor of about 1,000, flickers on timescales of minutes. Trying to photograph it is like taking a long-exposure image of a candle flame that changes shape every heartbeat. Still, the EHT, a global network of radio telescopes from Chile to Hawaii to the South Pole, took on the challenge. Over several nights in 2017, it collected petabytes of data, synchronizing observations with atomic clocks accurate to a billionth of a second. Then began 5 years of analysis, calibration and modelling, until finally, in May 2022, the image was unveiled. At first glance, it looked familiar. Another golden ring, another darkness in the centre. But this time, the darkness was ours, the very heart of the Milky Way. The glowing ring measured about 51 microarc seconds across. To put that in perspective, it's like seeing a donut on the surface of the moon from Earth. That ring corresponds to a physical diameter of roughly 60 million kilometres, or about 37 million miles, close to the size of Mercury's orbit. Inside that ring lies the event horizon, the point of no return. The light we see doesn't come from the black hole itself, but from superheated gas spiralling around it at near light speed. Magnetic fields twist and compress the plasma until it glows in millimetre wavelengths. The black hole's immense gravity bends that light into a ring, its near side appearing slightly brighter because the gas there moves toward us, boosting its emission through relativistic beaming. That faint asymmetry, that shimmering curve of light, is the outline of Einstein's theory made visible. The first time humanity has truly seen the consequence of space-time folding in on itself. And yet, the EHT image was not a photograph in the ordinary sense. It was the result of combining data from 8 telescopes using a technique called very long baseline interferometry. Each telescope recorded radio waves separately. Only later were they combined using atomic clock timing to reconstruct a single coherent image. The process required modelling assumptions about the orientation of the magnetic field, the distribution of plasma, even the geometry of the accretion flow. In other words, what we see is both measurement and model, data and interpretation. The EHT team ran millions of simulations, testing every possible configuration until the results converged on a consistent picture. The outcome matched predictions beautifully, but it also reminded us how much we still don't know. For instance, Why is Sagittarius A star so faint? For a black hole surrounded by gas, it radiates remarkably little energy. Theorists suspect the accretion flow is radiatively inefficient. Most of the heat falls into the black hole rather than escaping as light. In simpler terms, our galactic heart is a gentle eater, nibbling at cosmic crumbs rather than devouring them. Another mystery lies in its spin. Is Sagittarius a star rotating rapidly, dragging space-time around with it like water swirling down a drain? Or is it relatively slow? The data can't yet say. Future EHT observations, especially at shorter wavelengths, may resolve finer structures, even the twisting of magnetic fields near the event horizon. Still, even without every detail, the implications are immense. That blurry ring confirmed decades of inference. The orbits of the S-stars, the radio compactness, the gravitational pull, all converged on the same truth. There is a supermassive black hole at the center of the Milky Way, about 4 million solar masses, roughly 1% the mass of the galaxy's stars inside 3,000 light-years. It holds the inner galaxy in its gravitational grasp, influencing orbits far beyond what we can see. And yet, for all its power, it's small compared to the galaxy around it. If the Milky Way were the size of North America, Sagittarius A would be smaller than a grain of sand at its center. Its gravity shapes our motion subtly but surely. Our Sun and its planets orbit around the galactic core once every 230 million years. One galactic year that carries us through spiral arms, past star nurseries, and back again. Each time Earth completes such an orbit, entire epochs of life unfold and vanish. The black hole itself, meanwhile, changes only slowly. It feeds occasionally when a cloud of gas drifts too close, releasing flares of X-rays that ripple through the central region. Otherwise, it sits quietly, a patient anchor in a turbulent sea. The EHT picture is not the end of the story, but the beginning of a new era. With each new observing campaign, the network grows, adding telescopes, increasing resolution, capturing polarization that reveals magnetic fields threading the plasma. Already, scientists are planning next-generation arrays that could produce moving images of Sagittarius A star, showing the accretion flow changing in real time. Those sequences could test Einstein's theory in regimes never before accessible, probing whether spacetime behaves exactly as general relativity predicts. We may even use these observations to measure how the black hole's spin aligns with the Milky Way's bar and disk, clues to how it grew over billions of years. Did Sagittarius A star build up slowly, feeding on gas drawn inward by the bar? Or did it form early, a seed from the galaxy's infancy? Each answer reshapes our understanding not only of our own galaxy, but of black holes across the cosmos. There's a strange irony in it all. At the center of this vast whirlpool of stars, where gravity is strongest and matter moves fastest, there is also silence. No sound, no light, no solid surface. Only the steady curvature of space-time and the slow infall of matter. From chaos, calm, from motion, stillness. The black hole is both destroyer and preserver. It devours, but it also stabilizes, anchoring the orbits of billions of stars. In myth, the heart of the world was always a sacred void, a place where creation and destruction meet. In science, the metaphor endures. Sagittarius. A star is the void that holds the Milky Way together, the quiet point around which everything turns. It's easy to feel distant from such scales, millions of solar masses, millions of years, but in a way this discovery brings the cosmos closer. When you look up at the summer sky and trace the Milky Way arcing from horizon to horizon, you're seeing the faint outskirts of that same structure whose core now has a face, a ring of fire surrounding a shadow. And it's humbling to remember that all of it, the telescopes, the equations, the decades of measurement, began with curiosity about a faint radio signal in 1951. From that whisper came one of the most profound realizations in modern science, that the universe we inhabit is not only stranger than we imagined, but far more precise. Every orbit, every photon, every data point fits the pattern that Einstein wrote a century ago, the pattern of curved space-time. We've turned theory into sight. We've looked into the center of our own galaxy and found not chaos, but order, not brightness, but a shadow that proves the light around it is real. So when you hear the phrase Sagittarius A star, don't think of it as just another object catalogued in the sky. Think of it as the quiet signature of the galaxy itself, the period at the end of the Milky Way's long sentence of stars. Everything we are, every atom and orbit, ultimately circles that invisible point. And in that realization lies a kind of peace. Even in the heart of darkness, the universe holds its shape. Even in silence, there is rhythm, and sometimes, to see the light, we first have to find the shadow. At the heart of the Milky Way, where gravity bends space like a lens, there is a cluster of stars performing one of the most extraordinary dances in the universe. They orbit not an ordinary mass, not a glowing sun or a swirling nebula, but an invisible abyss. Sagittarius A star, the black hole at the galaxy's center. Each of those stars moves in an ellipse of breathtaking speed and precision, their paths warped by a gravitational field millions of times stronger than the one that binds our own planet to the sun. This region, just a few light days across, is called the S cluster, a tightly packed family of stars whipping around the black hole in a gravitational ballet. To the eye, through a powerful telescope, they appear as flickering points near the center of the constellation Sagittarius, indistinguishable from the countless stars around them. But when observed over years, their motion becomes unmistakable. They trace orbits so small, so fast, that only an object of unimaginable mass could hold them in place. The closest of these stars move at speeds of up to 8,000 kilometers per second, about 5,000 miles per second, roughly 3% of the speed of light. It's difficult to imagine what that means. A jet aircraft moves at around 900 kilometers per hour, 560 miles per hour. These stars move nearly 10,000 times faster. If one of them orbited at Earth's distance from the Sun, it would complete a full revolution in just a few hours. Among them is the star astronomers call S2, the most famous member of the cluster. It's about 15 times the mass of the Sun and twice as hot glowing blue-white, with surface temperatures near 28,000 degrees Celsius, about 50,000 degrees Fahrenheit. Yet from Earth, it's too faint for the naked eye, buried beneath 26,000 light-years of dust and gas. Every 16 years, S2 completes one full orbit around Sagittarius A star, following a path so elliptical that it swings from about 1,800 astronomical units at its farthest point to just 120 astronomical units at its closest. At that nearest approach, known as pericenter, S2 hurtles through space at nearly 8,000 kilometers per second, about 5,000 miles per second, a velocity beyond comprehension. In that moment, the gravitational field it experiences is about 10 billion times stronger than the pull of Earth's gravity at its surface. Every atom in that star, every photon of light it emits, is slightly stretched and slowed by the curvature of space-time itself. The light leaving its surface must climb out of the black hole's gravitational well, losing energy as it escapes, a phenomenon known as gravitational redshift. We can actually measure this. As S2 races past its closest point, its light shifts subtly toward longer wavelengths, the visible spectrum sliding toward red. It's the same effect predicted by Einstein's general relativity more than a century ago, now observed not in equations, but in a real star. To make such measurements, astronomers needed precision beyond anything achieved before. The two research groups that dedicated their lives to this, Andrea Gaze's team at the University of California, Los Angeles, and Reinhard Genzel's team at the Max Planck Institute for Extraterrestrial Physics, spent decades refining the art of seeing through the turbulence of Earth's atmosphere. Using adaptive optics, they could correct the twinkling of starlight in real time, reshaping their mirrors hundreds of times per second. With that technology, they managed to track individual stars near the galactic center with an accuracy of mere milliarc seconds, the equivalent of resolving a coin on the moon. Year after year, they plotted points on the sky, each one a measurement of position, each one a whisper of motion. And slowly, the pattern emerged. Ellipses, arcs, accelerations. The The S-stars were orbiting something invisible but enormous. From their motion, the teams calculated the mass enclosed within their orbits. About 4.3 million solar masses, all contained within a region smaller than our solar system. That number couldn't be explained by any cluster of normal stars or by dark matter alone. There was only one possibility left: a supermassive black hole. In 2020, the Nobel Prize in Physics was awarded for this work. Half went to Roger Penrose, who had proved decades earlier that black holes are inevitable predictions of general relativity. The other half went jointly to Andrea Ghez and Reinhard Genzel for providing the strongest evidence yet that such an object resides at the centre of our own galaxy. Ghez became only the fourth woman in history to receive the Nobel Prize in Physics. Her team had turned patient observation into proof, transforming theory into sight. The S cluster, however, is more than a confirmation of theory. It's a laboratory where the laws of physics are pushed to their limits. Near Sagittarius, a star, space-time is not flat, but deeply curved. Newton's tidy ellipses no longer apply. Orbits precess. They shift forward with every revolution, tracing rosettes instead of closed loops. This effect, called relativistic precession, was first detected for Mercury's orbit around the Sun, where the shift is just 43 arc-seconds per century. For S2, it's 12 million times stronger, a measurable wobble visible within a single human lifetime. When S2 made its most recent close pass in 2018, the observed precession matched Einstein's predictions almost perfectly. No other explanation fits the data. Close to the black hole, time itself behaves differently. The stronger the gravitational field, the slower time passes relative to an observer far away. If you could hover beside S2 as it swept past pericenter, your clock would tick ever so slightly slower than one on Earth. The difference would be tiny, a few minutes over 16 years. But it's real. This is gravitational time dilation, another consequence of relativity confirmed by the motions of these stars. And deeper still, near the event horizon, the effect becomes absolute. Imagine a small spacecraft falling towards Sagittarius A star. To an outside observer, its descent would appear to slow, its signals stretching longer and longer, redder and redder, until they fade into silence just above the event horizon. Time, from our perspective, would seem to stop. But to the traveller inside the ship, everything would appear normal, until the tidal gravity tore atoms apart. The difference is not illusion, it's geometry. Time and space are woven together, and near a black hole, that fabric bends so steeply that down and future become the same direction. What we see in the orbits of the S cluster is the gentle outer edge of that phenomenon, the part we can still watch without falling in. Each star is both a clock and a test particle, tracing the curvature of space-time itself. By comparing their periods, velocities, and redshifts, astronomers can test general relativity more precisely than ever before in a region of strong gravity. So far, Einstein is still undefeated, yet the data also hint at mysteries. Some of the S-stars, like S4711 and S4714 discovered in recent years, orbit even closer than S2, completing a revolution in just 7 to 10 years. Their paths suggest that the gravitational field may be slightly asymmetric, perhaps influenced by the distribution of dark matter or clusters of faint stellar remnants near the core. The black hole is not alone. It sits in a swarm of gravitational companions, each tugging, each leaving faint signatures in the dance. From our distant vantage point, 26,000 light-years away, we watch this ballet through telescopes so sensitive they can detect the motion of a star no larger than a pixel. It's like observing a grain of sand orbiting another across an ocean and still measuring its path to within a few centimeters. Every night of data adds another brushstroke to the map of the galaxy's heart. It's humbling to think that this region, no bigger than our solar system, holds the key to so much of cosmic physics. Here, within a volume that would fit comfortably between the Sun and Pluto, 4 million suns worth of mass compress space into a gravitational well from which even light cannot escape. And yet, around that abyss, stars still dance. Gravity bends them, but it does not destroy them. They trace the line between existence and oblivion, showing us where physics becomes poetry. For the astronomers who study them, this dance is more than data. It's a kind of communion with the fundamental nature of reality. Andrea Ghez once described it as watching physics in action. Each orbit is a test of our deepest understanding of how the universe works. Each photon of starlight, stretched and delayed, carries information about the curvature of space-time itself. And for the rest of us, the listeners, the dreamers, it's a reminder that even in the depths of a galaxy, there is movement, rhythm, and balance. The Milky Way doesn't merely exist, it performs. Its heart keeps time, not with beats or pulses, but with orbits. 16-year cycles of stars racing through darkness, tracing the invisible hand of gravity. If we could see it with our eyes, the sight would be unforgettable. A cluster of brilliant blue stars whirling through an amber haze, moving so fast their light bends slightly as it travels to us. Each would flare in brightness as it approached the black hole, then dim as it receded, a cosmic heartbeat, measured not in seconds, but in centuries. In the centre, no star, no light, only a faint ripple in the air where space curves inward. We are unlikely ever to stand there or witness it directly, but we can imagine it. And perhaps imagination is enough, because everything we've learned so far about the S-cluster, about Sagittarius A star, about the bending of time and the dance of stars, began with imagination followed by persistence. Telescopes turned to the same patch of sky year after year, seeing just a few faint dots, until those dots revealed the hidden rhythm of our galaxy. Time itself stretches and swirls in that region, yet through careful observation we've managed to capture it, to measure the very slowing of time predicted by Einstein a century ago. In the galactic heart, the flow of time is not uniform. It ripples and bends with gravity. Every orbit of S2, every pulse of light from its surface is slightly delayed, slightly curved, a reminder that the universe does not tick at the same rate everywhere. When you look up at the Milky Way tonight, the faint band of light arching over you, you're seeing the outer disk, stars like ours, scattered across 100,000 light-years, but hidden in that brightness. The true heart beats more slowly. There, seconds stretch, orbits twist, and light itself struggles to escape. Yet even in that extreme, the laws of nature remain elegant, coherent, precise. The universe, in its most violent places, still dances in time. The closer we move toward the heart of the Milky Way, the more the quiet patterns of spiral arms dissolve into something wild. The smooth lanes of starlight give way to turbulence. A region dense with gas and dust, alive with radio waves, magnetic arcs, and the echoes of ancient explosions. Here, gravity and chaos coexist. It's a part of the galaxy where stars are born, where others die, and where everything between them drifts through a constant storm. This inner realm is known as the Central Molecular Zone, or CMZ. It spans roughly 1,500 light-years across, a kind of molecular ring wrapped around Sagittarius A star. From Earth we can't see it in visible light. To our eyes it's hidden behind clouds of interstellar dust thick enough to block almost every photon. But in radio and infrared wavelengths it shines like a furnace. This is the Milky Way's engine room, dense, hot, and in perpetual motion. The CMZ contains about 60 million times the mass of the Sun in gas and dust, enough raw material to make hundreds of millions of new stars. But unlike the serene star-forming regions in our spiral arms, like the Orion Nebula or the Eagle Nebula, this environment is far more extreme. Temperatures here can reach 50 to 300 Kelvin, minus 220 to plus 25 degrees Celsius, or minus 364 to plus 250 degrees Fahrenheit, plus 77 degrees Fahrenheit, much hotter than typical molecular clouds elsewhere in the galaxy. The gas is under enormous pressure, often more than 10,000 times higher than in the solar neighbourhood. Every cubic centimetre of space here contains hundreds to thousands of hydrogen molecules, while in the space around our Sun, that number is usually less than 1. It's not just dense, it's restless. The gas in the central molecular zone moves at speeds of tens of kilometres per second, tens of miles per second, stirred by turbulence, gravity, and magnetic fields. Filaments of plasma, long glowing threads of charged particles, arc above and below the galactic plane like glowing ropes stretched by invisible hands. These filaments can span tens of light years, yet remain astonishingly narrow, sometimes less than a single light year wide. Their radio emission betrays powerful magnetic fields running through them, perhaps 100 times stronger than the magnetic field near Earth. One of the most famous of these is the radio arc, discovered in the 1980s. It stretches vertically across the galactic center, a luminous structure of synchrotron radiation, light emitted by electrons spiraling through magnetic fields at nearly the speed of light. The arc cuts through the central region like a beam, intersecting a ring of glowing gas clouds called the arches and the quintuplet clusters, two of the most massive and densely packed star clusters in the galaxy. Each contains thousands of young, hot, massive stars, some shining more than 1,000,000 times brighter than the Sun. These stars are so luminous that their radiation carves cavities into the surrounding gas, pushing it outward like wind in a storm. But despite the abundance of gas, the galactic center forms stars far less efficiently than expected. This has puzzled astronomers for decades. If you have enough material to make hundreds of millions of suns, why aren't they forming faster? The answer lies in the environment itself. The gas clouds here are constantly buffeted by shock waves, the aftermath of supernovae, the outbursts of massive stars, and even the occasional flare from Sagittarius A star. These shocks compress the gas in one moment and tear it apart in the next. Gravity tries to pull matter together. Turbulence fights to scatter it again. The result is a kind of cosmic tug-of-war where only the densest knots manage to collapse and ignite. In places where that balance tips, new stars are born. One of the most remarkable nurseries is a vast, twisted cloud known as the Brick, or G0.253 plus 0.016. It's one of the densest molecular clouds in the Milky Way, nearly 30 light-years across, containing more than 100,000 solar masses of gas. Its average density is about 10,000 particles per cubic centimetre, and inside it, temperatures hover around 60 Kelvin, minus 213 degrees Celsius, minus 351 degrees Fahrenheit. Yet strangely, it's almost completely dark in infrared. Despite its mass, it shows little sign of active star formation. Astronomers think the Brick may be caught in a delicate balance, squeezed by gravity, but held up by turbulence and magnetic pressure, teetering on the edge of collapse. Other clouds in the region are less shy. The SGRB-2 complex, located about 400 light-years from the black hole, is one of the largest and most active star-forming regions in the galaxy. It's a colossal ball of gas roughly 100 light-years across, filled with protostars, masers, and chemical complexity that borders on the bizarre. Radio telescopes have detected more than 60 different molecules there, including simple alcohols, amino acid precursors, and even molecules of sugar, glycolaldehyde. In a way, it's a cosmic chemistry lab, mixing carbon, oxygen, nitrogen, and hydrogen into the ingredients that someday may form planets. And perhaps life. These molecular clouds orbit Sagittarius A star in an elongated ring, roughly 100 parsecs in radius, about 330 light-years. Their motion isn't smooth, it's chaotic and clumpy, more like a string of beads on a twisted wire. Simulations suggest that gas streaming along the Milky Way's bar is funneled inward until it reaches the CMZ, where it stalls, collides, and piles up. Those collisions trigger waves of compression, lighting up the ring in bursts of star formation before fading again. It's a cycle that may repeat every few million years. A heartbeat of creation and destruction around the galactic center. Threading through all this chaos are the magnetic fields, invisible lines of force shaping the motion of gas and dust. In the CMZ, these fields are strong enough to influence the entire environment. They can channel plasma into filaments, stabilize clouds against collapse, or accelerate cosmic rays that produce synchrotron radiation. When observed in polarized radio light, they reveal ordered patterns running parallel to the galactic plane in some places, rising vertically in others. It's as though the entire region is woven from magnetic threads. Among the most striking features are the non-thermal filaments, slender, straight lines of radio emission stretching for tens of light-years. They were first discovered in the 1980s, and their origin is still debated. Some scientists believe they trace magnetic flux tubes illuminated by high-energy electrons. Others think they mark shock fronts or boundaries between regions of different plasma flow. Whatever their cause, they are unique to the galactic center. No other part of the Milky Way looks quite like this. Amid these threads and clouds are the scars of ancient explosions. Supernova remnants like SGRA East expand through the region, their shock waves ploughing into nearby gas. SGRA East is particularly dramatic. A shell-shaped cloud about 25 light-years across, filled with hot plasma heated to millions of degrees, roughly 10 million Kelvin, about 9,999,700 degrees Celsius, or 18 million degrees Fahrenheit. It's believed to be the remnant of a massive star that exploded about 10,000 years ago. The blast was powerful enough to compress surrounding molecular clouds, possibly triggering new generations of stars while disturbing the delicate gas flows toward Sagittarius A star. This interplay of explosions and gravity gives the galactic center its character. Every event leaves ripples that shape the next. When a supernova detonates, it sends shock waves crashing into molecular clouds, heating and compressing them. The densest parts collapse into new stars, while the rest is blasted outward to feed the surrounding medium. Those new stars eventually explode, and the cycle begins again. The CMZ, for all its violence, is a self-sustaining ecosystem, and in the background always the black hole, Sagittarius. A star feeds only occasionally, but when it does, its influence ripples through the region. Flares of X-rays and infrared light burst from its surroundings, sometimes lasting only minutes, sometimes hours. These outbursts can double or triple the luminosity of the central region. X-ray echoes reflected off nearby clouds show that such flares have occurred in the past, one particularly bright one about 200 years ago. If we had been watching then, the core of the Milky Way might have shone as a faint additional star in our night sky. In 2010, NASA's Fermi telescope discovered giant lobes of gamma-ray emission rising above and below the galactic plane, each stretching nearly 25,000 light-years into space. They were named the Fermi bubbles, and their origin remains a mystery. Some believe they're the remnants of a powerful jet or outflow from Sagittarius A star, others that they come from an era of intense star formation in the CMZ. Either way, they testify to how much energy flows through the galactic heart, how even brief events there can shape structures tens of thousands of light-years away. If you could stand near the edge of the central molecular zone, impossible of course, but imagine, the sky would be bright with motion, nebulae glowing in infrared, filaments stretching like luminous veins, and clusters of massive blue stars burning with impossible brightness. The temperature would vary from the freezing cold of molecular clouds around 50 Kelvin, minus 223 degrees Celsius, minus 370 degrees Fahrenheit, to the blistering plasma of shock-heated gas at millions of degrees. Magnetic storms would ripple silently, their charged particles tracing arcs invisible to human eyes. It would feel both alive and unstable, a galactic storm in slow motion. And yet, amid that chaos, there is order. The turbulence follows patterns. The magnetic fields, though tangled, guide the flow of gas. The star-forming clouds orbit in resonance with the Milky Way's bar, keeping time with the galaxy's rotation. It's as if, even in the most extreme regions of the cosmos, physics insists on harmony. The center of our galaxy is not a void, but a living system, a cycle of energy, matter, and motion, all driven by gravity's unrelenting hand. It's easy to think of space as empty, but here, within just a few hundred light-years, space is anything but. It's thick, luminous, magnetic, and dynamic. Every particle is part of a greater rhythm. Shock, collapse, flare, and calm. When we look into this region through radio or infrared eyes, we're peering into the beating heart of the Milky Way. Not the still, silent heart of Sagittarius A star, but the vibrant, swirling storm that surrounds it. It's here that the galaxy breathes, creating and destroying, condensing and dispersing, recycling matter endlessly in a cosmic loop that's been running for billions of years. And within that turbulence, perhaps without even knowing it, the seeds of future stars, and maybe of future life, are already waiting. If you could watch the Milky Way from far above, from a place outside space and time, you would see its spiral arms sweeping outward like the slow turn of a cosmic pinwheel. But your eyes would be drawn not to the arms, but to the structure that anchors them, the luminous bar cutting through the center. From that vantage point, the bar would seem alive, rotating slowly, its stars and gas streaming along curved, elliptical paths. It looks serene, almost symmetrical, but in motion, it's anything but static. It is a cosmic conveyor belt, moving matter inward, shaping the galaxy's fate, one rotation at a time. To understand the bar's role, imagine the Milky Way as a vast disk of stars and gas orbiting a shared center of gravity. In an ideal, perfectly symmetrical galaxy, everything would move in circular paths. But real galaxies are rarely ideal. Over time, gravity amplifies even tiny irregularities, and as stars interact, their orbits stretch and twist. When enough of them align in a particular pattern, their combined gravity begins to influence the rest, forming a dense, elongated structure, the bar. The Milky Way's bar is about 27,000 light-years long, rotating once every 100 to 120 million years. The stars in it move at speeds of around 200 kilometers per second, about 125 miles per second, following paths that loop outward and inward in a graceful oscillation. To the human eye, it would seem like a solid structure, but it's really a wave of density, a gravitational pattern made visible by the stars it guides. As the bar rotates, it exerts torque on the surrounding gas in the inner disk, pushing and pulling, creating a slow inward drift of material toward the galactic center. This process is remarkably efficient. Interstellar gas clouds, initially orbiting peacefully in the disk, encounter the bar's rotating gravitational field. They lose angular momentum, that is, they spiral inward, in much the same way that water spirals toward the drain in a sink. The gas doesn't fall straight in, it follows curved paths, forming shock fronts along the leading edges of the bar where density builds up. Those shocks compress the gas, triggering bursts of star formation. In this way, the bar acts like a galactic pump, drawing gas inward and transforming it into new stars as it goes. Some of that gas eventually reaches the inner few hundred light-years, where it collects in the central molecular zone, the dense, turbulent region we explored before. There, the inflow feeds not only star formation, but occasionally the black hole itself. Every few tens of thousands of years, a cloud drifts close enough to Sagittarius A star to be partially consumed. Most of it is torn apart, flung away by tidal forces, but a fraction of it spirals inward, heating to millions of degrees and releasing powerful flares of X-rays and radio waves. Those rare moments of feeding are the direct result of the bar's work. Matter shepherded inward across tens of thousands of light-years, slowly funneling toward the abyss. In simulations, this behavior emerges naturally. When astronomers model spiral galaxies on supercomputers, starting with rotating disks of stars and gas, bars appear spontaneously. They form when the disk's rotation becomes dynamically unstable, when the balance between gravity and centrifugal force tips just slightly. Stars begin to align in elongated orbits, creating an asymmetric gravitational potential that drags more material into alignment. In just a few 100 million years, a full bar can appear, stretching across the galactic core. Once formed, the bar changes the galaxy's entire metabolism. It redistributes angular momentum, pulling material inward and pushing some outward. This fuels the central regions while clearing out gas from the mid-disk, altering the rate and location of star formation. It also helps create the spiral arms themselves. The ends of the bar act like anchors for the spirals, setting their pitch angle, the degree to which they wind around the galaxy. The Milky Way's two primary arms, the Scutum Centaurus and Perseus arms, are thought to emerge directly from the ends of the bar. Bars don't just move gas, they also shape time. Over billions of years, the bar's rotation slows as it transfers angular momentum to the outer disk and to the dark matter halo surrounding the galaxy. The stars inside the bar, meanwhile, migrate, some moving inward toward the bulge, others outward into the disk. This stellar migration mixes the chemical composition of the galaxy, spreading heavy elements forged in earlier generations of stars across vast distances. It's one reason why the Milky Way's disk shows such complex gradients of metallicity. And bars themselves evolve. They grow, strengthen, and eventually dissolve. When a bar first forms, it tends to be thin and rapid. As it ages, it slows and thickens, developing the boxy or X-shaped bulge seen in infrared light. Eventually, if too much mass builds up in the center, either from star formation or inflowing gas, the bar can weaken and vanish, restoring a more circular symmetry. Then, in time, new instabilities can form another bar, starting the cycle again. This cycle of formation and decay can repeat several times over a galaxy's life. Simulations suggest that our Milky Way may not be on its first bar. An earlier one might have existed billions of years ago, dissolving as the inner bulge grew dense, only for the current bar to re-emerge later. Each generation leaves its mark in the distribution of stars, in the thickness of the bulge, and in the orbits that define the inner galaxy. Other galaxies show the same process playing out on grander scales. Take NGC 1300, a barred spiral galaxy about 61 million light-years away in the constellation Eridanus. It's one of the most photogenic bars in the cosmos, a perfect symmetrical spine stretching across its luminous disk with spiral arms unfurling gracefully from either end. Through telescopes like Hubble, NGC 1300 looks like an artist's rendition of cosmic order, calm, balanced, and beautifully structured. But simulations reveal that its inner regions are anything but still. Gas streams along the bar, forming shock fronts that glow in hydrogen alpha light, twisting and compressing before spiraling into a miniature ring of star formation around its nucleus. In the very center lies a smaller bar, a nuclear bar, nested inside the larger one, rotating at a slightly different speed. This bar-within-a-bar configuration acts as a second-stage conveyor belt, moving gas all the way down to the galactic nucleus, perhaps feeding a central black hole much like ours. Another striking example is NGC 1365, located about 56 million light-years away in the constellation Fornax. It's often called the Great Barred Spiral Galaxy, and for good reason. Its bar stretches over 100,000 light-years, nearly the full width of the Milky Way. At each end, vast spiral arms curl outward, filled with regions of intense star formation. In the center, a ring of newborn stars encircles a supermassive black hole estimated to be about 2 million solar masses. The gas feeding that black hole flows along the bar, guided inward by the same gravitational torques that sculpt the spiral arms. When astronomers observe it in infrared and X-ray wavelengths, they see a vivid picture of the galactic engine at work. Gas funneled inward, forming stars, lighting up, then falling silent as it's consumed. Galactic bars like these are not rare. They are, in fact, common. Roughly 2/3 of all spiral galaxies in the nearby universe possess them. That statistic alone tells us something profound. Bars are not peculiarities. They are phases, natural stages in galactic evolution. They represent a kind of gravitational self-organization, a way for galaxies to rearrange themselves, to redistribute matter and momentum. Without them, galaxies might stagnate, their gas stranded in the outer arms, never reaching the central regions where new generations of stars and planets could form. The bar, in other words, is the galaxy's circulatory system. It carries the lifeblood of gas from the periphery to the core, keeping the inner regions alive. Without it, the Milky Way's center might be far quieter, its black hole starved, its central clusters dim. Because of it, we have the central molecular zone, the arches cluster, the quintuplet cluster, and the bursts of star formation that light up the galactic bulge. From a broader perspective, bars also act as cosmic historians. Their shape, rotation speed, and orientation record the internal evolution of their galaxies. By comparing galaxies of different ages, astronomers can trace how bars grow longer and slower over time. Some simulations even show that as the universe expands and galaxies interact less frequently, bars become more dominant. the universe growing calmer yet more organized in its old age. The bar of the Milky Way, seen from our perspective within the disk, is hard to visualize directly. But data from infrared surveys like Spitzer 2MASS and Gaia have revealed its structure in exquisite detail. It stretches roughly 27 degrees from our line of sight, its nearer end pointing toward the constellation Scutum. The stars within it are mostly old, billions of years in age, yet young stars are being born along its edges, where gas compresses and forms clusters. At its core, the bar merges smoothly with the bulge, forming the X-shaped pattern seen in infrared. It rotates with serene inevitability, driving the slow inward flow of gas that sustains the galaxy's heart. And in that slow motion lies an echo of cosmic patience. Over 1 billion years, the bar may move gas across just a few thousand light years. It doesn't rush, it doesn't need to. Gravity, after all, has all the time in the universe. If you could accelerate time, watch the Milky Way's bar over billions of years, you would see it breathing, growing, fading, reforming. You would see waves of gas sweeping inward, igniting bursts of stars that flare and fade. You'd see the black hole feeding, resting, and feeding again. The galaxy would seem alive, pulsing with a rhythm far slower than any heartbeat, yet steady and eternal. And that is perhaps the quiet truth hidden in the bar's graceful symmetry. It is not just a structure of stars. It is a process, a bridge between creation and consumption, between the outer calm and the inner chaos. The bar at the galaxy's heart is a reminder that even in the cold mechanics of gravity, there is something that resembles life, a constant cycle of movement, exchange, and renewal. If the Milky Way's center is a stage of cosmic drama, full of dust, stars, gas, and gravity, then our telescopes are the instruments that let us see the performance at all. Without them, the heart of the galaxy would remain forever hidden behind veils of interstellar dust, silent and dark. To the naked eye, the direction of Sagittarius looks ordinary, a bright patch of the Milky Way, yes, but not remarkable. Yet beyond that faint glow lies an entire world invisible to human vision. It's only through the delicate art of collecting other kinds of light that we've learned to see through the darkness. The human eye is a narrow interpreter. We see wavelengths from roughly 400 to 700 nanometers, a tiny fraction of the electromagnetic spectrum. The rest, radio waves, microwaves, infrared, ultraviolet, X-rays, gamma rays, lies beyond our senses. But to the universe, those frequencies are just as real as colour or shadow. Every wavelength carries a different story about what lies behind the dust. The region around Sagittarius A star is a challenge unlike any other. Visible light cannot penetrate the billions of particles of carbon, silicate, and ice suspended across thousands of light years. Even the brightest stars near the core are dimmed by a factor of over 1 trillion. But infrared light, with its longer wavelengths, can slip between the dust grains. Radio waves can pass straight through them. And so, to uncover the Milky Way's heart, we built instruments that see what we cannot. Time machines in metal and glass. The first of these great eyes in the infrared was Spitzer, launched in 2003 by NASA. Spitzer was cooled to just a few degrees above absolute zero, about -268 degrees Celsius, -450 degrees Fahrenheit, to eliminate its own heat from contaminating the observations. It carried a mirror 85 centimeters wide and 3 instruments designed to measure light from 3 to 180 micrometers, far beyond what the eye can perceive. For 17 years it drifted silently in space, trailing behind Earth in its orbit, watching the universe in warmth instead of brightness. In 2004, Spitzer began one of its most ambitious projects, the GLIMPSE survey, short for Galactic Legacy Infrared Mid-Plane Survey Extraordinaire. It scanned the entire plane of the Milky Way in 4 infrared colours, capturing over 800,000 individual images. When stitched together, they revealed a panorama of our galaxy unlike anything seen before. Rivers of red dust, filaments of glowing gas, and the brilliant X-shaped bulge of the central bar. In visible light, that region was black. In infrared, it burned with detail. Spitzer showed that the Milky Way's bar extended farther than we thought, and that young star clusters were being born even within the dustiest zones. Each of those faint points of light carried information about temperature, density, and composition. Infrared spectroscopy, the study of how matter absorbs and emits infrared light, became a kind of fingerprinting tool for the galaxy. From the patterns of emission lines, scientists could identify molecules like carbon monoxide, ammonia, and water vapor. Even more remarkably, they could estimate how fast the gas was moving. Every spectral line is shifted slightly depending on motion, stretched to longer wavelengths if the source moves away, red shifted, or compressed if it moves toward us, blue shifted. By mapping those shifts across the sky, astronomers could create kinematic maps, 3D models of how gas flows through the galactic core. In these maps, the bar appears not as a static object, but as a living current. Gas streams along its length, slowing and piling up near the ends, then curving inward toward the nucleus. Shock fronts appear as abrupt changes in velocity, cosmic traffic jams where the gas collides and compresses. Infrared spectroscopy turned the invisible geometry of the bar into a visible motion, giving us our first real glimpse of the Milky Way's internal weather. As Spitzer looked outward, another observatory, Herschel, went further into the cold. Launched by the European Space Agency in 2009, the Herschel Space Observatory carried a 3.5-metre mirror, the largest ever flown for an infrared telescope. It observed longer wavelengths than Spitzer, reaching into the far infrared and sub-millimetre range. That's the realm where cold dust and molecular gas glow most brightly. If Spitzer showed us the heat, Herschel showed us the chill, the raw material from which stars form. Herschel's cameras revealed networks of filaments threading the Milky Way's core like veins, each one dense with potential stars. In one survey called High-Gal, it mapped the entire plane of the galaxy, detecting more than 100,000 dense clumps of gas and dust. Many were on the verge of collapse, ready to ignite nuclear fusion and become stars. In the central molecular zone, Herschel saw a chaotic scene. Warm dust at 50 to 100 Kelvin, minus 223 to minus 173 degrees Celsius, or minus 370 to minus 170 degrees Fahrenheit. Minus 280 degrees Fahrenheit tangled with colder material just a few degrees above absolute zero. From that mixture, astronomers could trace how gas flows inward under the influence of the galactic bar, feeding both star formation and, indirectly, the black hole itself. Where Spitzer and Herschel revealed the glow of dust, radio telescopes like ALMA, the Atacama Large Millimeter/Sub-Millimeter Array, showed us its fine structure. ALMA sits high in the Chilean Andes, over 5,000 meters, 16,400 feet, above sea level, where the air is thin and dry. It consists of 66 antennas, each up to 12 meters wide, working together as a single instrument through the technique of interferometry. By combining signals from multiple dishes, ALMA achieves the resolution of a telescope many kilometers wide. With this precision, ALMA can map the motions of individual gas clouds near the galactic center. It can detect the subtle rotational signatures of molecules like carbon monoxide and hydrogen cyanide, tracing flows of gas only a few light-years across. One of its most striking discoveries was the mini-spiral, a set of curved, filamentary structures of gas orbiting within just a few light-years of Sagittarius A star. These filaments twist inward toward the black hole, illuminated by ultraviolet radiation from nearby massive stars. ALMA's data revealed the gas temperature, typically around 10,000 Kelvin, about 9,700 degrees Celsius or 17,500 degrees Fahrenheit, and its velocity, sometimes reaching hundreds of kilometers per second, hundreds of miles per second. It's the closest we've come to watching the black hole's feeding process in action, but ALMA's real gift lies in its ability to detect time itself. By observing the same regions over months or years, it can see the slow drift of gas, the changes in brightness as clouds pass behind or in front of the black hole. In that sense, it's not just a telescope, it's a chronometer, capturing the dynamics of the galactic core in real time. To understand how all these layers connect, stars, dust and motion, astronomers rely on Gaia, the European Space Agency's astrometric mission launched in 2013. Unlike infrared telescopes, Gaia observes mostly in visible light, but with extraordinary precision. It measures the positions, motions, and brightness of over 1.8 billion stars, constructing a 3D map of the Milky Way. Even though the galactic center itself is too obscured for Gaia's optical instruments, the data from surrounding regions, the stars in the bar and bulge, reveal its gravitational influence. By tracking how those stars move, Gaia has allowed astronomers to model the bar's rotation speed, its orientation, and even the streaming motions that show how gas flows toward the inner regions. When Gaia's optical precision is combined with infrared and radio data from Spitzer, Herschel, and ALMA, the result is like peeling an onion of darkness. Each wavelength reveals a different layer. Infrared sees the warm dust. Submillimeter and radio detect the cold gas. Optical maps trace the motion of the stars themselves. Together, they build a multi-dimensional picture, not just of where things are, but of how they move, how they evolve, and how they connect. The process is a bit like performing a CAT scan on the galaxy. Instead of slicing through a body with X-rays, astronomers use different wavelengths of light to slice through layers of dust and gas. Each slice corresponds to a different temperature, density, or velocity. When all those slices are combined, the galaxy emerges not as a flat image, but as a living, breathing structure in motion. And now, a new eye has joined the watch, one that extends our vision further than ever before. The James Webb Space Telescope, launched in 2021, is the most powerful infrared observatory ever built. Its segmented mirror, 6.5 meters, 21 feet wide, gathers more light than any previous space telescope. It operates at cryogenic temperatures near minus 233 degrees Celsius, minus 388 degrees Fahrenheit, protected by a vast 5-layer sunshield. Though Webb's primary mission is to look at the early universe, it has already turned its gaze toward our own galaxy's core, and what it's found is breathtaking. In 2023, Webb captured images of the Sagittarius C region, a star-forming cloud about 300 light-years from the center. In mid-infrared light, it glows with filaments, bubbles, and ridges, structures invisible in any other wavelength. The telescope's resolution revealed hundreds of protostars embedded within the dust, some still in the earliest stages of collapse. Spectroscopy with Webb's NIRSPEC instrument detected the presence of complex organic molecules and shock-heated gas, showing just how turbulent starbirth can be in such an environment. But beyond its stunning imagery, Webb provides data with exquisite precision. By measuring the absorption and emission of molecules in the infrared, astronomers can deduce not just temperature and motion, but composition, whether the gas is rich in carbon, oxygen, sulfur, or silicon. This chemical information helps trace where the material in the galactic center came from, whether it's the recycled remains of past generations of stars or fresh infall from the outer disk. When we look at these composite images, data from Gaia for stars, ALMA for gas, Herschel for dust, and Webb for infrared structure, we're not just seeing different parts of the spectrum, we're seeing different eras of time. Light at radio wavelengths may have left its source decades ago, infrared photons, centuries, visible light, thousands of years. Each frequency pierces a different depth into the galaxy's history. When scientists say these telescopes are time machines, it's not poetic exaggeration. They literally let us see moments separated by ages, all superimposed in one image. In a sense, we have built a new kind of astronomy, one where seeing no longer means looking, but decoding. We don't see the Milky Way's heart the way we see a mountain or a tree. We interpret it through spectra, velocities, and maps. The invisible becomes visible not through light alone, but through frequency, the language of the universe translated into soundless color. Every telescope adds a new voice to the harmony. Spitzer's warmth, Herschel's chill, ALMA's hum, Gaia's precision, Webb's clarity. Together, they turn the galactic center from a mystery into a melody of information. Each frequency hums with a different truth. Where stars are forming, where gas is flowing, where time itself seems to stretch. And all of it, all this complexity, all this beauty, was hidden just behind a veil of dust until we learned to look with eyes that never evolved in nature. From the moment we first pointed a dish towards Sagittarius in 1951 and heard that faint radio hiss, to today's orchestra of telescopes spanning continents and orbits, we've been lifting the curtains of our own blindness. We can now see the galaxy's heart, not as a dark unknown, but as a place of motion, of birth, of physics in its purest form. It took nearly a century to go from a whisper on the radio to a portrait in infrared, and yet, in cosmic terms, that's no time at all. We are only just beginning to see what the universe has been doing all along. When we talk about the Milky Way's heart, about Sagittarius A star, the swirling dust, the glowing gas, and the bar that threads through the core, it's easy to forget that we're part of it. Our sun, quiet and golden, is one of the billions of lights caught in that vast, rotating dance. We don't sit still, and we never have. Every day, every night, as we look up at the stars, we are moving, slowly, inexorably, through the grand current of the galaxy. The numbers are staggering. Our solar system lies about 26,000 light-years from the galactic centre, orbiting in one of the Milky Way's spiral arms, the Orion arm, sometimes called the local spur. It's a minor branch tucked between two great lanes of stars, the Perseus arm farther out and the Sagittarius arm closer in. From here, we have a diagonal view inward toward the bar, through clouds of dust and the constellations of Sagittarius and Scorpius. When we see that hazy stripe of the Milky Way stretching across the night sky, we're really looking into the cross-section of our own disk, toward the luminous core that anchors it all. Our sun, along with every planet, comet, and drifting piece of space rock bound to it, moves around the galaxy at about 230 kilometers per second, 143 miles per second. It's a number so vast that we have no everyday equivalent. At that speed, Earth travels the distance from the Sun to Pluto in about 4 days. And yet, even at such a pace, a single orbit around the Milky Way takes about 230 million years. In that time, life on Earth has transformed completely. The last time our solar system was in this same position relative to the galactic bar, the continents were fused together in the supercontinent Pangaea, and dinosaurs had not yet evolved. We have made about 20 full orbits since the Sun was born 4.6 billion years ago. That means we've travelled through every corner of the galaxy's spiral arms many times, through regions of gas and dust, through empty space, through places where supernovae once shone brighter than moons. Our entire history, all of human civilization, all of written memory, spans less than 1/1,000,000th of a single galactic year. We often imagine the Sun as fixed, the planets turning around it like clockwork. But in truth, the entire solar system moves together through the galaxy, like a small fleet drifting within a much larger current. The planets orbit the Sun orbits the galactic centre, and the galactic centre itself drifts slowly through the universe's web of gravity. It's motion within motion, within motion, an infinite nesting of paths. If we could somehow look down from above to watch our galaxy's rotation over millions of years, the Sun's orbit would appear as a slow ellipse, not quite circular. It oscillates gently above and below the galactic plane, bobbing up and down by a few hundred light years every 30 million years or so, a kind of galactic breathing. This motion is caused by the uneven pull of mass in the disk. Stars, gas, dark matter, all tugging slightly out of sync. When the Sun crosses the midplane, we pass through regions where the density of material, and perhaps even the frequency of comet disturbances, is higher. Some astronomers have speculated that these oscillations might correlate with periodic impacts on Earth, though the evidence is far from conclusive. The path of the Sun also wobbles subtly as it orbits, influenced by the bar's gravitational potential. Unlike the nearly circular orbits of stars farther out, our solar system's trajectory is slightly elliptical, stretched by the bar's pull and the combined mass of the spiral arms. We don't orbit a perfect centre. Instead, we move through a rotating gravitational pattern, as if surfing through waves of starlight. The bar's gravity creates resonances, regions where the orbital speed of stars matches the bar's rotation speed. Our solar system lies just outside one of those resonances, in a relatively calm zone between the bar's corrotation radius and the outer spiral arms. That stability may have been crucial for the long-term habitability of Earth. Within those resonances, stars can migrate, slowly exchanging angular momentum, drifting inward or outward across thousands of light years. This stellar migration, driven by the bar and the spiral structure, gradually mixes the galaxy like a slow cosmic stirring spoon. It's one reason why stars of different ages and metallicities can be found side by side in the same region. Some of the stars we see in our night sky may have been born far closer to the galactic centre, while others began their lives much farther out. Even our Sun might not have formed exactly where it is now. Models suggest it could have originated several thousand light years closer to the core before migrating outward over billions of years. If that's true, then the solar system was born in a denser, more active part of the galaxy, among massive stars and frequent supernovae that seeded our protoplanetary nebula with heavy elements. The gold in your jewellery, the iron in your blood, the oxygen you breathe, all forged in that neighbourhood billions of years ago before the sun drifted to quieter suburbs. And now, here we are, still circling, still part of that same slow ballet. From our vantage point, we can't feel the bar's gravitational pull directly. The forces at play are immense but diffuse. Even though the bar contains billions of stars, their combined gravitational effect on our solar system is weaker than the pull of Jupiter on the Sun. What we experience instead is the broad, steady curvature of the Milky Way's potential. A force so constant it feels like nothing at all. Gravity doesn't just hold us down on Earth, it holds us in orbit around the galaxy. It shapes the space we live in so completely that we forget it's there. Yet the bar does more than move matter. It organises motion. It sets the pattern speed of the galaxy, influencing how gas flows, where stars form, and how spiral arms evolve. It's a kind of slow, rhythmic metronome for the Milky Way's life. And though we're far from the core, we still move in time with that rhythm. Every time the bar completes a rotation, about once every 100 million years, the Sun advances through its own orbit, weaving in and out of the galaxy's structural patterns. It's like two dancers circling the same stage at different tempos, always moving, never quite aligning, yet part of the same choreography. Over the course of that motion, the appearance of the night sky changes dramatically. Stars that today form the familiar constellations will drift apart. New ones will take their place. In 50,000 years, Vega will replace Polaris as the North Star. In 1,000,000 years, the constellations will be unrecognisable. In 10 million, the Sun will have moved far enough through the disk that even the spiral arms will look different from our perspective. And when we complete a full orbit, 230 million years from now, the entire face of the galaxy will have changed. Arms reshaped, clusters scattered, maybe even new bars born. To us, the night sky feels timeless. But in the galactic frame, it's fluid. It shifts and flows like water, each star drifting in its own eddy, its own arc through space. We're used to thinking of the cosmos as fixed, but we live inside its slow motion, a movement so vast and steady that our human timescales can't feel it. The Milky Way itself orbits within a larger structure, the local group, a small cluster of galaxies including Andromeda and the Magellanic Clouds. We are all bound together by gravity, moving through the expanding universe at roughly 600 kilometers per second, about 370 miles per second, relative to the cosmic microwave background. It's humbling to realize that our entire galaxy, bar and all, drifts like a single leaf in a cosmic river. The scale of motion is layered beyond imagination. Earth spinning, Earth orbiting the Sun orbiting the galaxy moving through intergalactic space. Every moment of stillness we feel is built atop an infinity of motion. And yet, that motion is not meaningless. The Sun's journey through the Milky Way may have influenced the story of life itself. As we pass through regions of higher cosmic radiation, through spiral arms filled with supernovae, the conditions for life on Earth subtly change. Cosmic rays, magnetic fields, comet perturbations, all of them vary as we travel through different neighbourhoods of the galaxy. Some scientists have even suggested that mass extinctions on Earth could correlate with passages through spiral arms, though the evidence remains debated. What is certain is that the galaxy's rhythm, the bar's slow spin, the arm's grand rotation, is part of the background tempo of our existence. It's strange to think that our lives, so brief, so localized, are taking place aboard a system drifting through space at 500,000 miles per hour, tethered to a gravitational structure 100,000 light-years wide, and yet the same forces that move entire galaxies also hold together the atoms in our bodies. Gravity doesn't care about scale. The pull that keeps your feet on the floor is a faint echo of the same pull that guides our orbit through the Milky Way. If you could pause time and look at the Milky Way from far above, you'd see the sun tracing a luminous path along the Orion Arm, following a gentle arc through the galactic disk. Behind it trails a wake of comets and dust, like the tail of a slow-moving firework. The bar, glowing faintly in the distance, rotates beneath us, driving the inner machinery of the galaxy. We are passengers on a moving world, part of a structure so large that we'll never see it from outside. But every night, when we look up, we see its edge. The light of the Milky Way that arches across the sky is ancient. Some of those photons left their stars thousands of years ago, some tens of thousands. They've travelled through dust, through time, through the silent geometry of gravity before falling into your eyes. That light is your connection to the bar, to the bulge, to the heart of the galaxy itself. It's a faint whisper from home, not the home of your birth, but the home of everything. We are used to thinking of our world as isolated, a blue marble drifting in an indifferent void. But the truth is richer. The galaxy holds us, moves us, and writes our position in its slow rotation. We are participants in a movement that began long before life and will continue long after it. Every breath, every thought, every moment unfolds while the sun makes its way around the bar, a silent pilgrim circling a heart we can barely see. And perhaps that is the most profound perspective of all. We are not at the centre of the Milky Way, nor at its edge. We are somewhere in between, balanced in a region calm enough for life, close enough to feel the pull of the bar, distant enough to watch it shine. From this vantage point, we are both observers and participants in the galaxy's story. The stars we see are our neighbours. The black hole at the centre is our gravitational anchor. We are, in every sense, of the galaxy. So the next time you look at the Milky Way, trace that faint arc of light and remember, it's not a band in the sky. It's the plane of your home galaxy, the thin disk of your own existence seen from the inside. You are living within one of those threads, orbiting the bar's immense current, moving through the universe on a journey so long it outlasts continents, civilizations, and species. You are part of the bar at the galaxy's heart, whether you realize it or not. Every structure in the cosmos, no matter how stable it seems, is temporary. Even the elegant bar that threads through the Milky Way's center, that vast gravitational spine of stars and gas, is not eternal. It, too, will someday fade. Bars form from motion, from imbalance, from the subtle drift of stars toward shared orbits, and for billions of years they endure, redistributing the galaxy's matter, stirring its gas, driving its evolution. But slowly, inevitably, their own success becomes their undoing. As they funnel material inward, the bar builds up mass in the galactic core, stars, dust, and dark matter accumulating until the inner gravity well deepens and the bar begins to lose its shape. The very process that gives it life, the inflow of gas, eventually chokes it. Simulations show that bars can live for a few billion years before weakening. They slow as they transfer angular momentum to the outer disk and the dark matter halo surrounding the galaxy. Their once elongated orbits become rounder, stars drift away from the organized flow that once defined the structure, and at last the bar dissolves, not in catastrophe, but in exhaustion. It fades back into the disk, leaving behind a thicker, boxy bulge and a more symmetrical inner galaxy, but this is not the end. Given enough time, new bars can form again from the same restless motions that birthed the old one. The Milky Way may already have gone through several such cycles. Each regeneration changes the galaxy's appearance, creating new waves of star formation, new bursts of energy, and new flows of gas toward the core. The bar, in that sense, is not a permanent structure, but a repeating phase, the heartbeat of galactic evolution. And far ahead, in about 4.5 billion years, the Milky Way's next great transformation awaits, a collision with the Andromeda Galaxy. Andromeda lies roughly 2.5 million light-years away now, moving toward us at about 110 kilometers per second, around 68 miles per second. On the scale of galaxies, that's a slow and stately approach, but it is relentless. Over the next few billion years, the two spirals will draw closer, their mutual gravity distorting each other's disks into long, tidal streams of stars. At first, the outer regions will interact, spiral arms stretching, gas clouds colliding, star formation igniting in brilliant bursts. Then, as their cores converge, both bars, the Milky Way's and Andromeda's, will twist and warp under the gravitational stress. Eventually, they will lose coherence entirely, replaced by a chaotic web of overlapping orbits. What remains will no longer be two barred spirals, but a single, massive elliptical galaxy, its gas mostly consumed or heated, its stars moving in random directions rather than in ordered rotation. Astronomers already have a name for this future creation, Milky Way. At the heart of that new galaxy will lie not one black hole, but two. Sagittarius A star with its 4.3 million solar masses, and Andromeda's central black hole, which is far larger, around 140 million solar masses. As their host galaxies merge, these two gravitational giants will fall toward each other, spiraling inward through a halo of disrupted stars. Their slow dance will release intense gravitational waves, rippling through space-time itself. Eventually, they will collide and merge, forming a single black hole hundreds of millions of times the mass of the Sun, a new gravitational anchor for the merged galaxy. When that happens, the bar will be long gone. Its stars will have scattered, its pattern erased by the chaos of the merger, but in a sense, its legacy will endure, because the bar's long history of funneling gas and feeding the core may determine how the new galaxy begins its life. The mass and spin of Sagittarius A star will help shape the behavior of the merged black hole, influencing its jets, its accretion, and its eventual quiescence. And what of us? By the time the Milky Way meets Andromeda, the Sun will be nearing the end of its own life, swelling into a red giant, consuming Mercury and Venus, and likely rendering Earth uninhabitable. Our species, if it still exists, will not be watching from the same world. But perhaps, if we endure long enough, we will see it from elsewhere, a spectacle across billions of stars, two galaxies blending into one, their bars dissolving like waves merging in the sea. From that distance, the transformation will not look violent. It will unfold over hundreds of millions of years, a slow, graceful waltz. The spiral arms will stretch into luminous bridges, the bars will fade, the cores will brighten, and finally, when the chaos settles, Milky Way will shine as a single, smooth, elliptical galaxy, its light golden, its structure calm. The era of bars will be over, replaced by quiet equilibrium. The cosmos never stops rearranging itself. Galaxies collide and merge, stars live and die, black holes join and grow. Each phase writes the prelude to the next. Our galaxy's bar is just one note in that cosmic composition, a beautiful, transient structure marking a particular rhythm in an endless song. Someday, billions of years from now, when future astronomers in some distant world study the merged galaxy that was once ours, they may find traces of the bar still encoded in the orbits of ancient stars. Subtle signatures of order in the midst of chaos, a fossil of structure in a sea of randomness. And perhaps they'll realize what we are only beginning to understand now, that the Milky Way's bar, like all things in the universe, was both fleeting and eternal, temporary in form, but timeless in meaning. When we look at the Milky Way, we see light arranged into form, arms, a disk, a bar. But beneath that form lies motion. Nothing in our galaxy is still, not even for a moment. Every star, every cloud, every photon is caught in a slow, deliberate drift. We tend to imagine the center of things as calm, like the eye of a storm, but the heart of the Milky Way is not a place of stillness. It's a place of continuous transformation. The galactic bar reminds us of that. It's both an engine and a messenger, showing how gravity shapes chaos into pattern. From billions of stars moving in apparent disorder, an elongated rhythm emerges, a self-organized bridge of motion and meaning. It is proof that the universe doesn't need design to create beauty. It just needs time. Every structure we've traced in this journey, the swirling arms, the dancing stars around the black hole, the filaments of dust and light, is temporary. Yet in their impermanence lies the poetry of the cosmos. Bars form, fade, and form again. Stars are born from dust, live briefly in brilliance, and return to dust once more. Even black holes, those symbols of finality, are not eternal. They evaporate over unimaginable spans of time. The universe, at every scale, is a story of creation through dissolution, an endless cycle of loss and renewal. The bar at the galaxy's heart doesn't defy entropy, it dances with it. It takes disorder and gives it shape, knowing that shape won't last. In its slow spin, it carries the gas that makes new stars, feeds the black hole that waits in the center, and then, as its purpose wanes, it dissolves, giving way to the next form. What seems like permanence from our perspective is, on cosmic timescales, just motion slowed down enough to look like structure. And we, small beings on a small world, are part of that same motion. We orbit the galaxy without feeling it, carried by forces so vast we can only measure them with equations and faith. Yet somehow we're aware of it. That awareness, that ability to look outward and imagine the dance we can't see, is perhaps the most remarkable part of all. The universe not only builds stars and galaxies, it builds eyes that can look back and wonder where they came from. When you think of the galactic center, the chaos of gas, the burning stars, the invisible black hole drawing light itself into silence, remember that it is not destruction you're seeing, but balance. From chaos comes order, and from order comes motion. Nothing lasts forever, but nothing is truly lost. Energy becomes matter, matter becomes light, and light becomes memory. Everything circles back. We exist in that circle. The atoms that make you, the carbon in your skin, the calcium in your bones, the iron in your blood, were once part of stars that orbited the galactic bar long before Earth existed. You are, quite literally, built from the Milky Way's past. You carry fragments of ancient supernovae, stardust, shaped by the galaxy's slow turning, and someday those atoms will return to the same current that carried them here, drifting again through the cosmic tide. The heart of the Milky Way isn't just a physical place. It's a metaphor for everything in motion, for time, for life, for the quiet inevitability of change. It reminds us that the center is never still, that equilibrium is found not in stopping, but in continuing. The bar will fade, the galaxy will merge, the stars will die, but the story will keep unfolding. There will always be another shape, another rhythm, another heart. So tonight, if you happen to look up and see the faint stripe of the Milky Way stretching across the sky, pause for a moment. That light, that misty glow, is your home seen from the inside, the edge of the great wheel you're spinning within. Somewhere deep within it, in the darkness of Sagittarius, the galaxy's heart is turning, and you are turning with it. No sound, no urgency, only motion, only time. And as the fire in your mind begins to quiet, let that thought linger. You are part of a galaxy in motion, a universe that never stops. It has no true center, no final destination, only the endless, graceful act of becoming. Sleep well, traveller of stars, you are already home.